So, hello everybody, good morning ladies and gentlemen. You're welcome to take your seats and welcome to this first session in the morning called the Forest Application Part 2. So as usual we have 5 presentations focused on this topic and a little reminder from the committee to use the Padlet of the conference to report your feedbacks and it will stay open also after the conference. So without any further delay, I would call to the lectern the first speaker, which is Michael Dembina from Jet Propulsion Laboratory, United States. And he's presenting estimation of mangrove forest vertical structure with UAV SAR and LiDAR data fusion using FreeSAR campaign data. Please, Michael.
So yes, I'm Michael Dembina, and I'd like to acknowledge my co-authors, Mark Simard, Richard Chen, Brian Stiles, Sasan Sachi, and Yunling Lo. And I'm going to be presenting today about estimating mangrove forest vertical structure with airborne PolInSAR and LiDAR data fusion using deep neural networks. So just to give an overview of my talk, I'm going to begin with an introduction and discuss some of the motivations behind this study. So why data fusion, why are we looking at mangrove forests in particular for this study? Then I'm going to talk about the data that we used and the study area. And then I'll talk about the methods, so how we configured the deep neural networks to estimate mangrove forest canopy height, using LiDAR data as training with PolInSAR input features. And I'll talk about the feature sets that we used as input and how the networks were trained. And then I'll talk about the results. So the idea behind this study was to compare kind of different network architectures and see how they performed. And so we looked at single baseline networks as well as triple baseline networks. And we also looked at using deep neural networks to estimate canopy height uncertainty in addition to just the canopy heights themselves, which was a good question for us because part of this study we wanted to look at how well a specific network trained only on mangrove forests would do at estimating mangrove forest canopy height, but also the reverse of that, how well would a general network do trained on all sorts of different forest types, how well would that apply to a mangrove forest in particular? And then lastly, I'll conclude. So the main motivation for this study was that in 2018, the US National Academies of Sciences, Engineering, and Medicine released their decadal survey, which gives targeted observations for potential future missions. And one of the targeted observables in the most recent decadal survey was called Surface Topography and Vegetation, or STV. And in that decadal survey, they observed that it was not very likely that a single platform or a single sensor type could meet all of the STV requirements in terms of accuracy, resolution, and coverage. So as part of that, they proposed that multi-sensor and multi-platform approaches were more likely to be able to achieve those goals. And so we're looking into data fusion of SAR and LiDAR data because we think that can improve the coverage of the LiDAR data and it can improve the accuracy of the PolInSAR data. And up there in the top right, you can see that's a picture from the STV concept showing some of the options in terms of multi-platform, multi-sensor architectures. And in the bottom right, there's a photo of mangrove forests in Pongara National Park, Gabon, which is our study area. So I took that photo in 2016 as part of the AFRISAR campaign. And mangrove forests are really interesting. They're very important ecosystems. They have a lot of They're extremely productive, they're very carbon rich. They're also uniquely threatened due to sea level rise and also human activities. Unfortunately, coastal regions are usually prime real estate for human development. And they're also interesting because their vertical structure is different than a lot of other forest types. You can see in the photo there that they have these above ground root systems in both Pangara National Park and in Manda in Gabon, where there are both mangroves. And you can see the study area on the map on the right here. So Pangara National Park is the area to the south of the estuary, and then Manda is the area on the top. And that's showing the airborne LiDAR Elvis RH98 height metric, which we used as the training data for this study. And we also used UAVSAR, airborne PolInSAR data that was collected during 2016 as the PolInSAR data. And to identify which areas were mangroves and which areas were not mangroves, we used a mangrove extent map from the Global Mangrove Watch. And all of this is publicly available data. I've listed the citations there. For the Global Mangrove Watch, there's a few different versions. So we used version 3, and they give multiple year mangrove extents. So we used the one from 2016, since that was the same year as the AFRISAR data was collected. So now I'm going to talk about the way we configured the network to estimate canopy heights. So we used deep neural networks consisting of an input layer, which was given the UAVSAR PolInSAR features as input, which I'll talk about on the next slide. And then we used 4 hidden layers with sizes of 10 nodes in the first 3 layers and 5 nodes in the last layer. And we did try testing larger networks, but there's a negligible improvement in performance that we found. So we just stuck with a pretty small network. Of course, the issue with getting a larger network is sometimes you can get better results, but the network will be less robust or prone to overtraining sometimes. So we stuck with this. And then we wanted to test 2 network configurations. So one using a single baseline of input data, and then the other using a triple baseline network. And in both cases, the KZ of the baselines are one of the input features. So the network knows the sensitivity between phase and height for a particular baseline, and we hope that that's part of what gets trained during the training process. So here's a list of the PolInSAR features that we used as input to the network. So the first one is just backscatter, pretty obvious, HH, HV, and VV backscatter. In linear units of power, we found that worked better than trying to give dB to the network. We also gave the interferometric covariance matrix itself. So for the single baseline network, all of the baseline dependent features, we only gave them once, but then for the triple baseline network, we gave the features for all 3 baselines. And then of course we gave the KZ for each baseline. We gave the high and low coherence magnitude, and by high and low, I mean the optimized coherences, so the estimated canopy dominated and estimated ground dominated coherence magnitude, as well as the phase center height of those coherences above the estimated ground. So we did do some PolInSAR processing to try to remove the topographic phase and do coherence optimization before we fed the input features into the network, to try to give input features to the network that we thought would be well correlated to canopy height as opposed to just random features. And then we also looked at using the coherence separation, I'm calling it there, but it's really just the distance on the complex plane between the high and low coherences and the high and ground coherences. And I should say for the ground coherence, we assume no temporal decorrelation of the ground surface. So the networks were trained using 0.1% of the airborne Elvis data randomly chosen from each scene, and then the rest of the Elvis data was used for testing. And then, so we trained 2 networks. One we trained only on mangrove samples as identified by the Global Mangrove Watch data. The other network we just trained on any valid Elvis forest heights in the training set. And then we also trained one network on just a general network. We had this from a previous study, but we wanted to compare that to the mangrove-specific network. And this more generalized network was trained on all of the sites where we have coincident UAVSAR and Elvis data. So there's 4 AFRISAR scenes listed there, which you may be familiar with. In addition to Pongar and Manda, where we have mangroves, there's also Lope and Rabi, which are inland forest. And we also trained it with some boreal forest data in Saskatchewan, Canada. And so we had 2 networks in terms of one mangrove network and one general network, and then we made two versions of each of those, one that just estimated the canopy height using the square error as the loss function, so pretty standard, and then another that estimated the canopy height and the canopy height uncertainty. And so the canopy height uncertainty was used to make a weighted mean square error, but to avoid the network just choosing a high uncertainty for every sample, the loss function is regularized by the mean uncertainty. So the network is penalized if it chooses high uncertainty. So the loss function is reduced by having a low uncertainty, but the network can choose, relatively higher uncertainty for some pixels than for others. So now I'll just jump into the results. So this is for the single baseline network, the mangrove specific network. And on the left, there's a map of the estimated canopy heights in Pangara and Manda for the mangrove areas only. And then on the right-hand side are density plots showing the UAVSAR canopy height estimates versus the Elvis RH98. Neither of these do that well, really, for the single baseline network. As I'll show later, the triple baseline networks, as you might expect, do perform a lot better than the single baseline network. I think that's especially true for Pangara. Pangara has a much wider range of canopy heights, so you wouldn't necessarily expect one baseline to be able to get a good height estimation performance across the full range of canopy heights, because there are very low canopy heights in the mangroves there, dwarf mangroves that can be 2 to 3 meters, but then you also have some of the tallest mangroves in the world, up to about 50 or even 60 meters. So there's a wide range of canopy heights in Pangara. In comparison, Manda, the canopy height range is much smaller, as you can see there in the top right plot. So moving forward, that was the single baseline network, but it didn't use uncertainty. And now this is the single baseline network, but we did add the uncertainty output. And so even though it's a single baseline network, this is really now kind of a multi-baseline solution. Even though the network estimates a canopy height for each baseline individually, based on the uncertainty output for each pixel, we choose whichever baseline the network thought had the best uncertainty. And you can see here on the right that if I go back real quick and then I go forward again, you can see that Pangara, the results improved a bit, as you might expect, over the wider range of canopy heights, using multiple baselines and weighting the baselines based on their uncertainty does give you performance improvements in Pangara. It doesn't really help in Manda. It actually makes the results worse. And I think it's important to point out that there are other ways to do uncertainty estimation with machine learning, but in this particular approach, now that we're allowing the network to not try to optimize the mean square error, but rather this weighted mean square error, that in situations where the data is probably well defined and is very close to the training set, you actually do a bit worse because the network's no longer trying to find the optimal mean square error for all of the samples. And so now this is the single baseline network, but it's the general model. So it's trained on a variety of forest types, and then we just applied it only to mangroves. And you can see the results here again are not very good. Again, they do get better for the triple baseline networks, which I'll show in a bit. And so this is kind of expected. We wanted to see, we did expect, of course, a performance gap between a network that was trained just specifically on the mangroves versus one that was a general model, trained on everything, but then tested on mangroves only. You can see Manda is quite overestimated in the top right there. Pangara is also overestimated over most of the range of heights, but then kind of saturates once you get to the upper range. And now this is, yes, 2 minutes. And so this one is a single baseline network with the uncertainty output added. And this is where the uncertainty output seems to actually improve the results quite a bit. Both of the errors get bigger. And so when you have a general model that isn't necessarily trained on the same data that you're using to test, that's when the uncertainty output from our results seems to give a much bigger improvement. And now I'll go forward to the triple baseline network. So this is the mangrove-only triple baseline network. And these results are much better than the single baseline network, as you might expect for both study areas, Manda 2.7 meter RMS error and Pangara 5.18 meter RMS error. And I'll go pretty quickly here, but again, this is the mangrove-only network, but with the uncertainty output added. And this one actually doesn't improve, again, over the just plain triple baseline network without uncertainty. The errors are very similar. But if I go forward again, now this is the general model. And as you can see, again, for the triple baseline, the general model does worse than the specific mangrove model. though it definitely does better than the single baseline network. So you have 3.1 meter RMS error in Manda and a 6.3 meter RMS error in Pongara. And again, adding uncertainty to the general model makes it do a lot better compared to adding the uncertainty to the specific mangrove-only model. So again, so with the triple baseline network with the uncertainty output, now you get 2.8 meters in Manda and 5.6 meters in Pongara, which is better than the general model without the uncertainty. And the next question we wanted to ask is, are the uncertainty outputs from the network reasonable? Do they actually match the errors? And the answer is yes. In an absolute sense, the uncertainty sometimes tends to underestimate the true error. As you can see in the bottom right plot, the error spread is much bigger than you would expect if the true sigma was only 5 meters there on the right side. But you can see it's kind of interesting if you look at the uncertainty map, and that's the minimum height uncertainty shown for each pixel. But you do see a clear transition when you go from the inland forest to the mangrove-only area. So the uncertainty increases quite a bit in the mangrove forest area. Okay, I'll skip this, but the idea was that we wanted to just compare with the interpolated training data to see if the networks did better. And they did for the triple baseline case, but not for the single baseline case. And just to wrap up real quick, we have some future work we want to do, continuing to test this with more training data and other types of machine learning approaches. And just very quickly, we do have some open postdoc positions at JPL. I was asked to shout out, so there's 3 of them up there. I have links and contacts for those if you're interested or know someone who might be interested. You can also just ask me, and I can point you in the right direction if you have any questions. And that concludes my talk. Thank you.
Thank you, Michael. So there's one question from Machi.
Thank you for a very interesting presentation. I have a question. So, are you planning to use any explainability methods in the future to better understand what features how they contribute, and so it's not a black box?
Yeah, no, I like that question. Yeah, definitely, I would like to do that. We did some previous work where we looked at, kind of like feature selection, like which features were weighted more highly and which features were better correlated with the output and things like that. And I'd like to do that for this study as well. We just haven't done it yet. Yeah.
Another question from Carl.
Thank you for your presentation. Just one question. What's your motivation to choose the AE or the network path for mangroves and not using the conventional 2-layer inversion? Because especially for mangroves, if somewhat it works perfect on mangroves.
Yeah, no, that's a fair question. So we did do some previous work where we had some trouble getting good results for the kind of standard inversion in these study areas in particular. I think one issue is definitely temporal decorrelation, which was a challenge for us, particularly in some areas where there was flooding and so on. So I think we wanted to try this to see if we could get better results this way than our previous model-based estimation. But you're right. I think I don't know, in the future, I think we would like to try maybe a kind of hybrid approach, like we saw presented yesterday between the model and the machine learning methods.
The only critical on mangroves on temporal acquisitions is the change of the water level,
yes,
which of course introduces a change on phi0. So this means that you cannot take this as a constant. But besides this, if somewhere the 2-layer model works, it works on mangroves at L-band.
Yeah, no, that makes sense. I should look into that, letting the phase change with the water level. That's a good point. Yeah, thank you. Thanks.
Thank you, Michael. So,
So the next speaker is Leah Albrecht from DLR, and she's presenting estimating forest structure change by means of waveless statistics.
Good morning, everyone. My name is Leah, and I'm going to present you some insights about my work on forest structure change. Now, this presentation is a cooperation with the Helmholtz Center for Environmental Research with our colleagues Rico Fischer and Andreas Ruth. I'm a PhD student at DLR, and my supervisor is Kostas. So first, let us start with the Tandem X mission. We all know that we have some pretty interesting results we can retrieve out of the Tandem X datasets. If we combine them with another dataset, for example, the JEDI mission, we can use those reflectivity profiles and invert the forest height with actually great accuracy. So over here you can see the forest height map required over the Amazonas region. And one of the more interesting findings, it's not only the forest height, but also the structural component of this forest height. So over here you can see a structure map, which has a spatial resolution of 100 meters. So we basically take the face center heights retrieved from the Tandem X mission and get a structural component out of it. And you can already see that within different forest patches, we have a different structural signature. Now we can even go one step ahead and map the structural signatures over time. So here you can see the difference between 2008 and 2020 and 2011. So you see that the structural differences vary over time, and you can see some logging events going on at those blue points. Now, those structural changes are not really straightforward interpretable, which basically means that we should go one step back and use a forest height model to really be able to interpret forest structure change. And for that, we use the Four-Mine model. The Four-Mine model was implemented by the UFZ. Over here, you can see on the top the biomass, accumulated biomass in a normalized manner. And on the bottom, you can see the different distribution of the trees. Now, in Four-Mine, every tree is modeled individually. They start growing from the very beginning, and on the lower left, you can see the forest after 10 years. In the middle, you can see the forest at 50 years, and on the right, you can see the forest distribution at year 450. And you see that we go from a very homogeneous forest on the left to a very inhomogeneous forest on the right. And we can also see some structural changes at this peak of the biomass. So we there have a structural change from a more dense to a less dense forest. Now, the Four-Mine model does not only map a natural undisturbed forest scenario, but there are also two disturbance scenarios. The first one is the logging scenario. So there is a logging event occurring periodically every 50 years. And you can see that the tree distribution starts from a more inhomogeneous forest. And after the logging event, 25 years after, you can see that the forest is already grown again to a more homogeneous forest. But if we compare it to the natural scenario, we can see that the biomass does not really get the same values. So even 25 years after the disturbance, we can still see the effects of the logging event. The third scenario is the fire scenario. The fires are more implemented in a random way. So we have bigger fires and smaller fires. And you can see that, in this part of the forest, we have a very inhomogeneous forest, and over here you can still see the effects of a previous fire. So we have a more homogeneous forest in this part. And then the fire occurs, and it leads to a very inhomogeneous forest. Now, if we want to estimate the forest parameters which correspond to the structure, we always have the problem that the structure is scale dependent. So if we take an estimation window from our face center heights retrieved by the Tandem X, we can see that if the window is too small, we have a lot of variation within those two windows. And this basically means that all of the forest will always look heterogeneous because the local heterogeneity will always dominate. On the other hand side, if I have a window which is too big, you can see that I somehow lose the sensitivity to my structure variability, because within those two windows, the face center heights also seem a little bit the same. And this is exactly the reason why I choose a multi-scale analysis. So in order to do that, I'm using the wavelet transformation. The wavelet transformation has its roots with the classical Fourier transformation. The main idea is that I have an input image and I decompose it to different coefficients. And with every level of my decomposition, I will decrease the resolution of the input image, which leads to a new representation of the image. So as an input for my analysis, I use the phase center height retrieved from ForeMind. As I explained before, ForeMind maps the forests individually, which basically means that for every tree, I can obtain a reflectivity profile, and then I can rasterize the data to a chosen resolution. For every resolution cell, for every pixel, I get then a reflectivity profile, and I will just compute the center of mass and obtain the phase center heights. Now, the wavelet transformation scheme is implemented as a filter bank. So I have a variation of low-pass and high-pass filters. The first filters over here are always a convolution by the rows, and the second filters are always a convolutions by columns. So if we, for example, take this coefficient image over here, we see that I first have to apply a low-pass filter on the rows and then the columns. And this basically means that I have a very smoothened version of my image, and this is exactly the reason why those coefficients are called the approximation coefficients. Now, on the other hand side, if you use this transformation scheme, you will end up with those three coefficient images, and those are the detail coefficients, and they map the details in a horizontal, in a vertical, and in a diagonal way. Now, in order to reduce the resolution at every step of the transformation scheme, we can either degrade the resolution of our image, or we can just upsample our filter to double the size. So if I start with a filter size of 5, the filter for the next resolution step would be a filter size of 10. Now, those are the results I got for the wavelet transformation scheme with the ForeMind data set. You can see the biomass plots I just showed before again. And you can see 3 different plots which show the wavelet variance. The wavelet variance is a squared sum of all of the detail coefficients. Now, on the lower left, I used an input resolution of 10 meters. You can see that in the natural scenario, the level 1 decomposition follows the biomass line over there. Now, what I forgot to say, since we upsampled the filter by the factor of 2 after every decomposition level, it means that we somehow change the size of the neighboring pixels that we want to compare. So if I have an input resolution of 10 meters, my wavelet coefficients at the first level will also come from the scale of 10 meters. Now, the wavelet coefficients of the second level, since I upsampled my filter, will then correspond to the resolution of 20 meters. The third level coefficients will correspond to the level of 40 meters, and the third level coefficients will then correspond to the 80-meter resolution. Now, if I look at the input resolution of 20 meter, which you can see over here, we can see those structural changes in the natural scenario that I explained before, because the forest gets less dense. And if I then decrease my input resolution to 50 meters, we can see that I almost lose the sensitivity to my signal. And I can only obtain really big fires with the smaller level coefficients over here. So the problem with the wavelet variance is now that we have some sort of ambiguity, because if you look on the left side, we can see the natural scenario, and we start from a very homogeneous forest, which we can see over here. Over time, the trees grow, but not in a very similar manner. So we have at the year 35 already some smaller trees and some bigger trees, and the variance increases. Now, if we go to the fire scenario, we can see that at the year of 468, we also have a drastic increase in the wavelet variance, but it's due to the fire disturbance, not due to the normal regrowth of the forest. So this is an ambiguity we just have to keep in mind while interpreting the data. And now comes the most interesting part of my presentation today. I also used the wavelet transformation scheme on some real TandomX dataset. For that, I choose a test site in Finland, near the city Kuopio. On the right-hand side, you can see the coherence map for that region. So we see a lot of lakes and some forested areas. And the main reason I chose Finland is because there is a low topography, so I know that I do not have a lot of topographic errors in my results. I did acquire 2 different TandomX images. The first one was from 2012 and the second one from 2018. And for this part, I used an input resolution of 20 meters. Now, if we look at the left side, you can see the image from 2012. And within the circle, you can see that there is a forested area. So we have a lot of volumetric decorrelation over there. And if we go to the coherence map on the right, we can see that the coherence is around the value of 1, which basically means that we have a surface area over there. If we go now to the wavelet spectrum, we can also see that on the left side, there's a lot of variance within those forest patch. And on the other side, we see that all of the variance is gone. So if we just make a difference map out of those 2 images, we would be able to obtain those logging events. Now, if we go to the wavelet variance with an input resolution of 10 meters, we can see some really interesting things, because now we can see that the wavelet variance really differs within the forest stands. And if we zoom in on that a little bit, we can see that we have a lot of variance in this area over here. And if we do a comparison with the Google Earth image from the same year, we can see that the forested area over here does have another spectral signature than the surrounding trees. So the trees over here are a little bit higher, and the surrounding trees are lower. And we can clearly distinguish those 2 structural variations. Now, if we go down to this part of the image, we can also see some very high variances over here in our wavelet variance image. And if you remember, as I said before, the regrowth of a forest also does have an increase in the wavelet variance. And if we go to the Google image, we can see that there are some lower trees over there, and the surrounding trees are a lot higher. And this indicates that there was some sort of logging or fire event going on some years ago. Now, to sum up my presentation, the forest horizontal structure is always a multi-scale problem. And it occurs already at small spatial scales, which requires a really high spatial resolution. Now, TandomX provides this high spatial resolution for us, and we can use the canopy height profiles as an input for this wavelet transformation, which can not only characterize, but also lead to an interpretation of the structural heterogeneity at the different scales. And the physical interpretation is still ongoing, but as you saw, it already has a lot of potential. So thank you very much for your attention.
Thank you, Ilya. Are there any questions?
So it's very nice work, but let's say that when it comes to spatial characterization or pass me the word classification, you need to compete with artificial intelligence today. So my question for you is, do you think that this human intelligence method, which I like, will compete with other techniques like deep learning or things like that? It's a very broad question, I know.
Honestly, I'm not sure how to reply to this. Because in every part of our work, we somehow have to compare with AI, so
Okay.
I'm sorry.
I think that reviewers of your paper will ask this, so maybe it's
And I would start
just a
thinking about it.
suggestion.
Yeah.
Okay, thank you.
Are there any questions? No? So thank you, Leah.
So our next speaker is Stefano Teobaldini from Politecnico di Milano, and he has a presentation called Tomosensor Sensitivity to Temperate Forest Above Ground Biomass at P and L band in the Tomosens ESA campaign. Please,
Okay,
Stefano.
so thank you very much. So good morning. I'm here to present this work actually on behalf of Patrick Bennett, who is a PhD student at Chalmers. We start with an overview of the Tomosens experiment. We have 3 more presentations of this using data from this campaign tomorrow. So we will sort of advertise this data set. So Tomosens was an experiment funded by ESA to support investigation of forested areas using tomography. It was flown at the Eifel National Park in the Kermeter area. So let me see if the laser works. Okay, so it was more or less here. This is the area that was investigated, so it's a hilly topography. We have dominant species like beech and spruce trees. Forest height is about from 10 to 30 meters. There are peaks of, I think, on the order of 40 meters. And above ground biomass have peaks up to 400 tons per hectare. The SAR dataset is, this is a quite rich dataset. We have P-band data, L-band data. We also have C-band data, but for today we just look at P and L. They are all fully polarimetric data, and for L-band we also have bistatic data flown with 2 airplanes. And the data set is complemented by terrestrial laser scanning, by different kinds of aerial laser scanning. So we have a conventional aircraft flown by XEGLOB, and then also some drones to investigate the forest structure locally, and we have a forest census at about 80 plots. Just a word about the flight plan. I told you that we have P-band and L-band. So for P-band, this was the flight plan. So basically, we have nominally 10 passes at 0 baselines, and then we go down about 4 meters every pass. So in total, we have 20 passes with a nominal horizontal scan of vertical scan of 40 meters. Why 10 passes with 0 baselines? Because we fly with very small aircraft. And so let's say that the wind is making the baseline for us. So it's just nominally 0. And this is at L-band. At L-band, it happens that we have two aircraft. So this is how they fly in this plane. This is the master, this is the slave, and basically they both transmit and receive. They are synchronized, and so we can get bistatic acquisitions. And also in this case, the master flies always the same trajectory, and the slave moves, so it goes down with a pattern. The along track separation was nominally some 20 meters. It had to be much more, on the order of 100 meters, because it was not safe for the pilot. And let's say that the product of this campaign is mostly this one. So it concerns the generation of tomographic cubes. So basically 3D data structure, which we also call voxels, where we have the intensity of forest scattering at different heights. And this is for P-band, for L-band bistatic, and in all polarization. So let's say that the thermosense provides us with, I think it is an important data set to characterize how the forest reacts to different bandwidth and different acquisition modes. Okay, here is the reference above ground biomass map. This was estimated from aerial laser scanning. This map was generated by XEGLOB. And basically what they do was to examine forest height as estimated by their LiDAR. And then they also ingested the information from the 80 plots. So we had information about forest height as measured on the ground, about DBH, about the tree species. We knew if the tree was dead or alive. And also some more sophisticated input came from TLS. So basically at selected plots, they could reconstruct the forest to within an unbelievable accuracy with the LiDAR. And they derived allometric information. So all of this was ingested to generate this biomass map. So we think it's pretty good. And also they had to, okay, let me say that the one problem was that at Kermeter biomass is very high. So they missed the lower end of the biomass range, and for this reason, they included some data from the Czech Republic, this area, the Silesian Beskids. They say that the forest type is pretty much the same. So we think it is okay. And matter of fact, this map has, let's say, if you compare the training data with validation data, the error is about 10%. So this is the accuracy of this map. And this red rectangle is the area covered by the radar. Forest type, let's say that dominant species are beech and spruce. So on your right here you have the forest type map in radar coordinates. Basically we have beech, spruce, and magenta indicates all the other it's mixed species, which we refer to simply as temperate forest. And so, based on this data set, we are presenting today, let's say, three main results. The first is an analysis of the vertical reflectivity profiles for different polarization, bandwidth, and acquisition mode as a function of AGB. And then we will present the AGB retrieval by PolInSAR using different methods and for different forest types, and also an analysis of the role of the gram slope. So all the analysis that I am going to show you are based on this grid here. If you have a very good sight, you can see that the dots are different colors, which indicate different forest species. And basically, we extracted the information from the radar or for the biomass at a scale of half an hectare. And by the way, this map here is radar intensity at L band, just if you integrate from 20 to 30 meters. So it's more or less the canopy intensity. Et voila. This is how the vertical profiles were analyzed. So basically, this is a top view. So just imagine that you have a number of plots. Those plots are classified according to their biomass given by the LiDAR map. And then we aggregate all plots within the same biomass class, say low, medium, high, and we average. So basically, we have a statistics of how the vertical profile is for different biomass classes. And here is some result. Now, it will take a while to comment on this. Here we have P-band, HH, HV, PV, and for spruce and for beech. And then L-band, again, HH, HV, VV for spruce and beeches. you see the different colors refer to different biomass classes. So I think it's very nice to see that blue, which indicates very low biomass, provides a vertical profile which always peaks at the ground. So it basically means that the vegetation is quite sparse and we get the main peak from the ground. As the biomass increases, so we pass from blue to red, you see that the profile tends to change. And in particular, we have that for spruce, there is a change in, let's say, the change in intensity is quite pronounced, whereas for beeches, there is more change in height. So let's say that not only the vertical profile are responding to increasing biomass range, but also it seems like there is a difference between the two different species. It's also nice to see that at P band, the ground peak is always stronger, at L band is weaker. So, okay, it means that we understand something about physics, and this is always a good news. But there is more physics to it. So keep in mind those panels here. This is L band monostatic. Here is what we get, L band bistatic. You see, we have less ground. So as predicted, in many papers, of course, but if we acquire bistatic data, then the ground gets weaker. And this is most likely because the ground peak in forested areas is triggered by double bounces. And so with bistatic data are less sensitive to it. Of course, it depends on the bistatic angle, but you see the trend is pretty much it. And this is the same for the mixed forest class, which we just called temperate forest. Now, this is how you can interpret the two. So let's say that you can imagine, so if you want to map the vertical reflectivity profile to how the tree actually looks like, you can take a look at this slide, more or less. So it is very qualitative, of course, but it provides an idea. So this is the increase that we have from a short spruce to a tall spruce, and you see the difference in the profile, and this is what should happen for a beach. So, ThermoSAR retrieval. Our ThermoSAR retrieval method is very simple. Basically, we fit an exponential function with just two parameters. So it's A0 and A1. We get those two parameters with a regression. And we use for the intensity different methods. So the method one, we take the total intensity. So it's the conventional SAR intensity. Method two, we just take the intensity of tomographic data from 20 to 30 meters. So we integrate within a range. Method three is the same as method two, but it is normalized by the total intensity. Okay, and we evaluate the usual metrics. 50% of the data are used for training and the rest for validation. And this is what we get, P band and L band for the total intensity. So you see there is some sensitivity concerning spruce, really pretty much nothing for beeches. And this is the total intensity. If we pass to the tomographic intensity, then we win sensitivity and everything improves. In this case, the error is pretty good. It's also true that the biomass range is not huge, so probably we are facilitated in this. What is interesting for me is this method, okay? That is the method number three. Basically, we take the tomographic intensity normalized to the total intensity. And you see that it's not bad at all. And I like this result, of course. This is just a single result at a single site, so I don't want to claim that we have invented anything, but this is interesting because if it turns out that we can work with a normalized radiometric indicator, then it means that we can build a mission that doesn't have tight calibration requirement. So I take this as a promising sign. And then finally, some analysis about the gram slope nuisance factor. This is a hilly topography. So basically, we have even quite steep slopes, and we know that it's not simple to compensate for it. Now, Patrick has implemented some radiometric correction for it. I don't know the details, but matter of fact, if we also limit this analysis to, so if we restrict the analysis to, by taking only slopes less than a certain figure, so let's say that here is less than 90%, less than 90 degrees, 20 degrees, and 10 degrees, you see that we have an improvement, especially at P-band, not so much at L-band, and frankly, I haven't exactly figured out why there is this difference. So just to sorry, and this is the final biomass map generated by the radar. Just to conclude, we have analyzed the vertical profile. For spruce, we have a strong growth in intensity and not so much in height. For beeches, it seems to be the other way around. So we have sensitivity to biomass and sensitivity to the forest species. We have decent AGB retrieval performance. Consider that the error of our map was estimated to be about 10%, so we are pretty close to it, and I don't think there is much more to do for this data set. And of course, we confirm what was known, that the gram slope is always a problem that has to be dealt with. And this concludes my presentation. Thank you so much.
Thank you, Stefano. Are there any questions?
So, hello, Stefano.
Hi, Matteo.
You showed the profiles, so I guess they were with the first one that you showed, the spaghetti. So I guess they were with the same height, and you changed the level of biomass.
Not the same height. Actually, it was mixed. Wait a second. Those are mixed. So,
okay. And if you fix the height, do you see the same thing?
If we fix the height, that's a nice question. So I can try to answer simply by a visual inspection of what I see now. If you fix the height, well, I can see the same peak, for example, here. So just to pick one. So I can see that the peak is more or less here, but we have a change in intensity. And this was observed for the spruce especially. So also the conclusion is that for spruce, we have a growth in intensity, whereas for beeches, more in height. So I would say that for spruce, if we fix the height, we should be sensitive to biomass, to the biomass change. For spruces, probably not so much.
And the second question is, in the moment that you fix biomass and you fix height, how much does your profile change?
Okay. This is something that we can investigate. We didn't look into this, okay.
Thank you.
When looking at the effect of slope on the effect on the height estimation, have you looked at the effect of aspect as well, or if the slope is facing towards your viewing angle or in the other direction, and if that causes more overestimation or underestimation?
Well, here we are analyzing. So here I admit I do not remember if this analysis is in both headings or in a single headings. So for forest height, we surely looked into both headings. And of course, if you do things correctly, and bear in mind that with these tomography cubes are, let's say, back projected on the ground, or geocoded on the ground. So let's say that if everything is done correctly, the forest height is not affected by it. So for forest height, I do not remember big trends. It's also true that one heading was more disturbed, probably by radio frequency interference. So it's not super simple to do this comparison, but biomass was also tested for both headings. And I think that we can generalize, what was that? This last point, that of course we have if we restrict the analysis to mild slope, this improve for the biomass.
Thanks.
And Stefano, just thanks. A quick question. Did you try biomass retrieval in the bistatic configuration, since we can expect significantly reduced ground contribution, perhaps?
Yes, we did. If I remember correctly, it is the one that works best.
The best among
yes.
Also among the monostatic?
If I remember correctly, L-band bistatic is the one that works best. I mean, it's not an order of magnitude better, but it is slightly better.
Excellent.
A quick one. So why are you fitting an exponential profile? That seemed to defeat the purpose of having multiple baselines, since that's valid on the assumption of the uniform volume, right?
Actually, this was Chalmers' choice.
Okay.
I think it was just a trade-off between a simple approach, yet an effective one. Maybe Maciek can...
Yeah, but that is just power law. So it is, you have X-context, you can just as well, right? Biomass load.
But is fitting the profiles... Okay. But it's fitting the profiles to the exponential, right? Or not?
No. It's just a linear model in the logarithms.
Oh, I see. Of the total.
Yeah.
I see.
Okay. Thank you.
So that's all. Thank you, Stefano.
The next speaker is Noelia Romero Puig from DLR, and her presentation is about addressing forest change by means of PolInSAR measurements at L-band and P-band.
Okay, so welcome from my side, and thank you, Chiara, for the presentation. So today I'm going to present the first analysis, the first results of this forest change. This is an currently ongoing activity that we are carrying out in our group together with my co-authors, Matteo Pardini and Kostas Papathanasiou. Matteo will have also a presentation addressing this topic, but more from a tomographic point of view tomorrow. So I will start right away with the presentation of the test sites and the LiDAR data, so the reference data that we can use here. We are observing a very well-known forest, the Tronstan temperate forest, which is located in the southeast of Germany. And this is a managed forest, therefore we have continuous measurements. So we have reference LiDAR data here. We are presenting the H100 heights over at 2016, and then we also have the heights at 2018, and as well the very recent ones from last year and 2022. So the purpose of the presentation is to address the changes in the forest. Therefore, what we can do from these reference heights is to get the height change maps. So this is what we do here, and then we can focus now. On the change map between 22 and 26, at 2016, sorry, which is a span over 6 years, and it covers also everything that we have in the SAR data. So if we come now to the side of the SAR data, we are using SAR data of the DLR searchborne system. Again, we are observing the Trondstein forest, and we have a very rich data set, which is fully polarimetric, and we also have several baselines. In this case, we have 3 campaigns. They do not exactly overlap the same years of the LiDAR reference data, but they are contained within the same time period. So we have a campaign in 2017, another one in 21, and another one in 22. And we have constrained the baselines here to these 4 cases. So in order to have common baselines to the 3 campaigns from 0 to 20 meters. And then we have here the representation of the EPSAR data. So these are the three master acquisitions, so the RGB Pauli images from the 3 campaigns at L-band. And we also have the data at P-band. So of course, at P-band, we only have the last 2 years, so at 21 and 22. And we already see here some differences in the RGBs, which indicate us probably there are some differences in the structure of the forest. So what we are going to try to do now is to characterize these differences by different methods, and also to try to link the differences that we see here already in the RGB images to the structural differences that we see in the LiDAR height change maps. So if we go now to the presentation of the methodologies that we are going to use for this, we can start on the side of the polarimetric information. So with polarimetry, we can perform a polarimetric change analysis. I will not go very deep into the details because this is already presented work, but we can make a polarimetric contrast measure between the first one and the second acquisitions, and then we can optimize this polarimetric contrast measure by means of a generalized eigencomposition, in which we obtain the maximum and minimum contrast from the eigenvalues and their associated polarization states in the scattering vectors. And therefore, how we can represent this polarimetric change analysis or this information, we do it by means of the polarimetric increase and decrease of the power ratios. And of course, we do not want to just remain on the polarimetric information. We also want to include the interferometric information. And we can come back to the interferometric side. We can build our multipolarization multi-baseline coherency matrix on the Pauli basis. And from here, we can express the PolInSAR coherences, as shown here in the expression. And we know that with PolInSAR, we are sensitive to the vertical structure of the scatterers in our vegetation scene, and therefore we can apply a physical model to represent our vegetation as composed of 2 layers, so as composed of a ground layer which has a localized response at the ground and more extended volume layer. And now what we want to do, we want to try to separate these contributions and try to simplify our scenario in order to further or to better evaluate the nature of these changes in each of these contributions. So for this, there are several methods, both single and multi-baseline methods. In particular, here now we're going to focus on a multi-baseline hybrid model-based SCAP ground and volume decomposition, in which we end up having the separate covariance matrix of the ground and the volume, which are a function or which are given by their interferometric coherency. So we have a method in which we can obtain the polarimetric information and also the interferometric information to help us tell us about the changes in the scattering, about the changes in the forest structure. So starting now with the results, we are going to first apply the polarimetric change analysis. We are going to perform everything first at L-band because we have the 3 campaigns, so we can use the L-band scenario as a reference for the P-band scenario. And then we can start with the representation of the power change ratios of the increase and decrease. So of course, here we can combine the 3 years, so we can make these different polarimetric change analysis between the year 2017 with 21, also between the 21 with 22, and covering the whole span between 17 and 22. Of course, what we see here in the increase and decrease power, so the increase is this first column, and the decrease we see it in the second one, is that we see a mix between the changes that are happening both in the backscatter intensity and also in the scattering mechanism. So the brightness of the images show the intensity or the power of the change in the backscatter, and then the color of the image shows the change in the scattering mechanism. So, of course, we need to interpret this, and one way that we can also try to learn what we are seeing here is coming also back to the eigenvalues of the decomposition. So coming from the first to the third row, we have the same analysis of each combination of the campaigns, and then from the first to the third row, we have each of the first, second, and third eigenvalues. And what we can see is that already the changes that we're showing more or less in the RGB images, we can better see them now with the polarimetric change analysis. And even if before, if we go back, even if before, it can be a bit tricky or a bit more difficult to see the changes or these clear cuts that we were seeing in the LiDAR height maps, we can also see them in the eigenvalues. So they are there, and we do have them. And the second thing that we can get from this eigenvalue representation is that, of course, we are at L-band, and we are observing a forest scenario. And this is a high entropy scenario. So we see this very clearly in the eigenvalue. So we see that there is not much difference between the power of the first eigenvalue compared to the power of the second and the third eigenvalue. So if we want to further analyze this or try to make our life easier, we can also think about what we can do with this methodology, and then we can normalize the scattering vectors. Therefore, we can go back to normalized covariance matrices and perform the polarimetric contrast analysis over the normalized covariance matrices, and these would be the results that we have there. So if we do this, of course, we are removing the absolute changes, we are removing the changes in the scattering intensity, and we will remain only in the changes in the scattering mechanism. So only we remove the changes in the brightness, let's say, and then we remain with the changes in the color, which are an indication of the changes in the scattering mechanism. And of course, we are in a high entropy scenario, so seeing changes in the scattering mechanisms at L-band over the forest can be a little bit more challenging, but we also see them better right over the surfaces, which show maybe with more colors here. So now, if we want to include the interferometry information, we come back to the interferometric coherences here at L-band. I was now presenting from left to right the 3 years, and first showing the coherences with a baseline of 5 meters. So with 5 meters, what we see here, we see some changes, but we may not be able to correlate them yet to the changes in the forest structure, because here at this short baseline, maybe the residual baseline correlation that we have is even larger than the possible change that we want to see. So what we can do is we can go to larger baselines in order to increase our sensitivity to the vertical distribution of the scatterers. And here we have a baseline of 20 meters. And then we can bring back our LiDAR height maps, our LiDAR change maps. I didn't say it before, but here we see that the 0 is in green, so 0 means no changes. Then we see the clear cuts from 26 to 22. They remove part of the forest, and then we see them with this negative change height, and then we see the growing of the forest of those parts that they didn't cut. We see them towards more orange and red colors. So now, if we compare or we go to the baseline, to the interferometric, to the baseline of 20 meters, to the interferometric coherence, we can see some areas, we can identify these changes. So, of course, these are single-pass acquisitions, so in absence of temporal decorrelation, because we have the FSAR system, and therefore we can corroborate that what we see here is volume decorrelation and it's not temporal decorrelation. And indeed, we see that in the 2016, we have here, for instance, this area with much higher coherence, and we know from the LiDAR map that this area of the forest is increasing in height, and when we see in the 2022, is a decrease in the coherence level. This decrease in the coherence level is associated by an increase in the volume decorrelation. So now the next thing that we are going to do, having this in mind, is to perform, so we go from the original RGB Pauli images I was just showing here in order to have the difference before we go to the decomposition of one master image of each campaign, and then we perform the multi-baseline hybrid model-based SCAPI decomposition, and then we get the covariance matrices of both the ground and the volume separated. So the first thing that we see is that we may be able to identify better the changes once we have separated both the ground and the volume components of our vegetation. And of course, in the ground, we see that we have more variability in terms of spatial variability. So, of course, any changes, any variability that is induced or coming from the topography will show in the ground component. But also, we also see more variability in the colors, which means we see more variability in the scattering mechanisms that we see in the ground. So this is, in principle, what we try to use now. We try to apply this polarimetric change analysis over each of these ground and volume components. And then we can come here, and this is exactly what we do. So for the example, I was just taking now the more extreme years that we have, so to evaluate the differences between the 2017 and the 22, and then we can back and we can perform this polarimetric change analysis of the ground and volume components, and these are the results. These are the power change ratios that we get. Of course, we need to take care with the interpretation, especially we have seen that the ground component is very noisy, so we need to see how we interpret these results. But one way to do this, we can mask out the non-forested areas, and then we can compare these results with the LiDAR height maps of the change. And then we can come here, for instance, I was taking the increment of the ground, and then we can see some, even if it is difficult because of the noisy nature of the ground, we can see some correlations with the change map of the LiDAR. So, for instance, we can see here in this area where the forest was growing, we can see a slightly better maybe increase of the ground in green, which can be an increase of the HV component, or we can come here to these plots. They seem to be growing in height, but not too much. So we see an increase in the ground component, maybe of the ground to volume ratio, of the diedral component, sorry, because it appears in red. So we're using the Pauli decomposition. And then, of course, we see also changes in the surfaces. So these clear cuts, we can also identify them in the component of the ground here. What a clear cut means, how does the polarimetric change analysis can interpret a clear cut in the forest? This is something that we need to think about. We can think that when we perform a clear cut, maybe the surface component increases and then the power of the ground decreases, and this is maybe what we are seeing there. We can do the same thing over the volume, and then this is very clear now, how we see all these clear cuts when we have removed the forest. We actually see them very well in the volume component as changes in the volume component, so with a large brightness. So we can do the same analysis at L-band, and this is going to be a little bit shorter because we only have 2 years now. And if we go first to the interferometric coherencies, we see an opposite behavior. So when we focus at the coherencies of 5 meters, here we see that, of course, at P-band, at a larger wavelength, we penetrate more, we penetrate in through the canopy layer, and we have a strong component coming from the ground. And this is why we have higher coherence at the forested areas with the vegetation. And then what happens at P-band is that the surfaces suffer more from SNR decorrelation. And then if we try to perform the same analysis, we come here first to the polarimetric change analysis over P-band. Here in the first row, we have the normal ratios, and then we also have the normalized results. So of course, if we compare them to the L-band data, we see that we have the intensity of the changes at P-band is larger, and this was expected. And if we normalize the result where before we all see everything was black over the forest, here maybe in the projector it's a little bit harder to see, but we see something more. We see something more purple. We see some more information that complements what we see at L-band. And then we can come back to the eigenvalues. If we compare what we have at L-band and P-band, we can corroborate that indeed at L-band, due to this stronger ground contribution coming, backscatter, then we see we lower a little bit the entropy of the scenario, so we have a slightly larger first eigenvalue with respect to the secondary and tertiary eigenvalues. And this is also what we see when we perform the polarimetric change analysis now over the ground and volume components. So at p-band, we have a decreased resolution, so it's harder to see the high frequency or the small details, but we can see the general overall increase in the changes that we can observe at p-band. And with this, I would just like to wrap up what we have just seen, and this is what I have already commented. So we are trying to derive methodologies to detect and characterize the changes that we see in the forest structure. So we can do this by using both polarimetric and interferometric information. So from the polarimetric side, at L-band, we have very high entropy scenarios where almost all the changes that are coming from intensity changes, from changes in the backscatter, but we have also, it's harder to detect at L-band changes in the scattering mechanisms, which can be a little bit easier to detect at p-band. And of course, with interferometry, we can help to separate these contributions and have a better or an easier interpretation of the results. And this is all I wanted to say, so thank you very much for your attention, and I'm very happy to answer any of your questions.
Thank you, Noelia. Are there any questions?
Hello, it's a very interesting presentation. So my name is Ji from MDA. So regarding the question, you try to compare the clear cut like a chain. So did you try use backscatter or try to compare the chain? Because you see the clear cut area, the backscatter should be very low. So you can see the twin chain immediately. So can you try?
We were seeing, but in the backscatter, you don't see all the changes. Maybe the very clear cuts, of course, you should see them in the backscatter. Other changes that if the growing or logging or individual removal of trees, then those are harder to see in the backscatter. So a very clear cut, you should see it in the backscatter, yes.
Okay,
yes.
Thank you.
You're welcome.
Hi there, thanks for the presentation. With this type of analysis, can you establish what proportion of, for example, the HH return comes from the canopy and how that changes?
Sorry, Sean, can you repeat the question?
With this type of analysis,
yes.
Can you work out what proportion of the HH return comes from the canopy, comes from the volume, and how that changes?
Of the HH, for instance, you want to take one polarization channel and say how it...
Yeah, so with this analysis, can you do that?
So I guess if you go, instead of the Pauli basis, you go to the linear basis and then you try to perform the polarimetric change analysis, then you should see the changes, the proportion of the changes in each of the polarization channels.
But would you be able to localize those to the volume as against the ground?
By using the polarization, if we can say that this is coming from the volume and not from the ground. Only identifying from which polarization channel is the change coming? Is this?
No, the reason I'm saying this is because there's a widespread confusion about what people are interpreting as volume scattering in the decompositions. Mm-hmm. And part of it is to do with identifying how much of the copolarized return is coming from the canopy. And I mean, if this sort of analysis can clarify that, it would make life a lot easier in interpreting the data.
Mm-hmm. Okay. I can look better into that also. Okay. No, thank you very much.
Sure.
Thank you.
Are there other questions? No? So, thank you, Noel.
Thank you.
So our last speaker is Kathy Unmesh from the Indian Institute of Technology, Indore, and is presenting SAR for change, deforestation detection using dual polarimetric SAR information. Please.
Hi, good morning. So This is work that is being carried out by Anam Sabir. She is a PhD student at IIT Indore, and essentially this is part of the work that we are doing for NISAR mission. We are trying to test what kind of algorithms will be useful to detect changes, and currently we are testing with the cumulative sums of change method that NISAR will probably use for deforestation detection. Just to use with spaceborne SAR data, we wanted to check what kind of frequencies and polarizations, how role they play to detect these changes, and what resolutions we can get the products out, and whether there is an impact of kind of the forest ecoregions or even the forest management types. So to do this, we started to see what kind of data we can collect over different test sites, and two of the sites that I'm going to discuss here are the Haldwani forest range, which is in at the foothills of the Himalayas, and this is a subtropical managed forest with deciduous species of teak and a few evergreen species of eucalyptus. The other major species is poplar, which is planted there since this is a managed forest, and this forest sees very frequent logging activity. Almost every year some part of the forest is logged and replanted. So it's a very dynamic forest. The other area is the forest in central Kalimantan, which is very close to the Palangkaraya, which is the zonal capital of this region. In Indonesia, and so this is more of a peat swamp forest, which is very tropical and almost evergreen. So these two test sites were chosen, and the inset boxes they show. I don't have okay. And this inset boxes they essentially show the extent of the ALOS-2 acquisitions. So coming to the data sets, we have the Sentinel-1 dual pole SLCs, which was acquired starting from 2016 all the way up to 2020. For Haldwani, and the 2020 dataset is currently being processed, so this will be updated soon. For L-band, we could acquire or could get strip map SLC datasets of ALOS-2 from 2016 to 2020. Over Haldwani, we had 23 acquisitions, and slightly more over Kalimantan, 28. So the numbers in the boxes below, they show the SLCs from Sentinel-1 acquired each year. So as you can see, 2016, I think at the around mid of 2016, the acquisition started. So they are half of the other acquisitions. And from 2017, we have approximately 28, 29 acquisitions each year. So in the processing, we use the ICE3 and ICE2 modules to read the respective data sets. For ALOS-2, ICE2 was used to read the SLCs, and then we packaged them back into HDF5 containers to kind of also emulate NISAR, which will also give the data in HDF5. For Sentinel-1, ICE3 has support to read the data sets, and then we transform them back into HDF5 containers. So once they are back into HDF5, we use the same DEM and made sure that they are all well co-registered to each other. So both L and C bands are co-registered to each other, and that helps us to generate the GSLCs at 25 and 100 meter resolutions. And then we extract the C2 matrix, the GCOVs from it. And so we get the co-pole backscatter, cross-pole backscatter. We also do have the C12 parameters, and we also use the dual pole alpha angle to test it. Two of the methods that we are currently evaluating one is the cumulative sums of change, which essentially only takes into account either the backscatter or in this case the alpha angle, and the other one is a sequential omnibus, which uses the Wishart test statistics at the back end, and the advantage with that is it can work on the C2 matrix. So some sort of polarimetric information might also be included in that case to see if we can improve our results. So currently I am focusing the results on cumulative sums of change. Sequential omnibus in our preliminary testing did not result in much improvement, but we are trying to understand it better. So probably we will have, in the next presentations, we will have a better approach. Just to give an overview of the two methods, I won't spend too much time here. Cumulative sums of change essentially takes the time series for a pixel, the backscatter, and we calculate the difference with respect to the long-term mean, and then those are cumulatively summed up. So wherever you have a change, the cumulative sum will drop, and we do a bootstrapping just to make sure that what we are seeing is not a one-off event, and it stays true with bootstraps. So I think in this case we tried to vary the number of bootstraps, but that did not have any impact on the accuracy that we got. So we have, I think, stuck to 100 bootstraps in overall across all the frequencies. In omnibus test, we have the null hypothesis, which uses the complex Wishart distribution. And as I said, the advantage is that we can use the P, which is the polarizations, can be full pole or even a single pole data. Now, the one question that we had is that how do we validate any change that we can see? So for Haldwani, it was slightly easier because this is a forest that we could access in India, and we have been to this forest since 2015 regularly, and we have managed to collect data about the plots which were logged off. So a lot of these plots are very small, about 1 hectare in size. We have intentionally not kept any plots less than 1 hectare because the resolution that we hope to get the products out is at 100 meters. So getting anything less than that would not be productive. The maximum area logged was 220, but for Kalimantan, there are change maps such as Hansen's change map, but again, those are from optical data sets which may or may not capture the change that SAR can see. For example, with cloud cover, we might not see any change that happens during the monsoons in these regions, but if there is a change, then SAR would capture. So we will unnecessarily have false positives in those cases. So one way to overcome this was to have a group of forestry guys and remote sensing people go through Sentinel-1 backscatter as well as to look at Landsat images and kind of collect the plots which changed. And so these were kind of the validation plots that we are using here. And the minimum area to maximum area is ranging from 4 hectares to 79 hectares. So one thing that we immediately saw was in case of Kalimantan, the logged area is much larger. And one of the reasons for that is that this area is actively under transforming from forest regions to either managed logged areas or to rice fields. While in case of Haldwani, it does not necessarily change the land use patterns, but it's only a cyclical change between having a poplar trees and then those being logged off and a new plantation coming up, and again they are logged off after 6 years. So for Haldwani, poplars are having a maturity of 6 years, while eucalyptus is logged off after 12 years. So those are the trees which are used for pulp making and then go on to making paper. Accuracy assessment, we use the standard parameters like overall accuracy and kappa coefficient. Mostly I will use the kappa coefficient to display the results here. So these are the change maps that we obtain at two resolutions. One is the 25 meter and the other one is 100 meters. So on the left hand side is at the top row is Kalimantan, C-band, VV and VH. And the bottom is Kalimantan L-band, HH and HV. So as we can see in this case that in case of HH, we can, many of the changes are well captured, but probably there are few changes which are not captured. That is on account of the less dense time series of at L-band that we have in comparison to C-band. In case at 100 meters is essentially capturing the same change, but a lot of smaller areas are removed or filtered out. In case of Haldwani, there is a lot of difference between C-band and L-band, the way that the changes are captured. If we see Haldwani C-band, a lot of these areas which were logged off have been captured, but in case of L-band, they are not. And that's a major one of the major issues with this. And one of the reasons we found from field data that we have collected is that there have been gaps of the order of 6 months to 8 months between two acquisitions at L band in many cases. And between that, whenever there has been logging, the new plantations have a backscatter which is much higher than what would have been at if it was barren. And so because of that, the cumulative sums does not have a change point significance as high as we would have liked if we had a denser time series. And so this, both irrespective of the resolution, we lose out on a lot of change that has happened. And this is not because of the frequency, but this is because of the way that the data is currently available with ALOS2. And this definitely affects the accuracy assessment. So here is the cumulative sums of change method at 25-meter resolution. We see the kappa coefficient at C and L band. So if we look at Kalimantan, we can see that for copole, L band has a better performance, but not at cross pole, while C band performs kind of well at cross pole. But for Haldwani, the performance is very bad. Essentially, we are, if we look at the overall accuracy, it is better because the positives and negatives are detected, but the problem is that there are a lot of false positives and false negatives in case of Haldwani, as I said, because of the absence of data at L band. But for C band, the problem seemed that, this is the same when if we, instead of 25 meters, we go to 100 meters, so at 1 hectare, which is something that NISAR will provide the products at. So at cross pole, L and C band perform equally well, and they exceed 0.8. So almost 80% of the time we have that this is not a chance of that we are detecting the change, but it's actual change. While at Haldwani, although the accuracy improves to almost kappa of 0.6 at C band, because of the frequency of changes that are happening in these forests, we are losing out on a lot of data sets. And also another problem that might be is that most of the LULC maps in these regions are not accurate. And so many of the non-forested regions are misclassified as forests. That can also result in C-band capturing a lot of change, which is on account of agricultural area, but it is mapped to forest. So just to show the overall accuracy, as I said, the overall accuracy, if we just look at the overall accuracy, then Sentinel at 100 meters has a decent accuracy. But if we look at the kappa coefficient, then at cross pole we have a good accuracy, but with L band we don't. So we tried a few different things. One of them was that we kind of tried to compensate for the seasonality, so we removed the trend that is there, and the overall accuracy improved slightly with kappa coefficient also having a slight increase, but this is something that we are still checking. And one of the last things that we tried was to see the effect of the logged area. So the size of the logged area has a lot of impact on how much accurately we can detect those changes. We have we divided the validation into two. One was areas which are less than 20 hectares, which are relatively smaller logging areas, and areas which are more than 20. So the one in purple color or orange color in this case is the areas which have, so for larger areas we see that the kappa coefficient is much higher than for smaller areas at both C band and L band, and at 25 meter and 100 meter. The impact at 100 meter is slightly different because for cross pole we are having a lower accuracy, and that we are still checking why this is happening. But one of the things is that probably there is a chance that we might be missing on detecting changes which are happening at for a very smaller regions, and we might be losing out on those deforestation events. And something similar is also observed for Haldwani. However, here the improvement in ALOS2 is there, And this shows that because a lot of the areas in Haldwani are very small, the overall accuracy is impacted by that. And if larger areas were there, then probably there was a better chance that we might have had a slightly improved accuracy. So just a few takeaway messages that in this case we are seeing that the logged area size and the frequency of logging activity, so essentially forest management types, have some effect on the detection of deforestation. The smaller regions, at least in case of Haldwani, were not captured at both L and C band as well. And the impact of logged area was much higher for L band data than C band data. However, in case of Kalimantan, both polarizations performed well, while in case of the managed forest of Haldwani, cross-pol data performed well. Few of the next steps that we are doing is to use coherence products to see if those can work better, or to integrate backscatter and coherence and see if we can have an integrated solution which better detects these changes. Before I conclude, I would just like to mention that we are organizing the India Geoscience and Remote Sensing Symposium this year, again, in December 2023, from 10 to 13 December. It's at Bangalore. And so you're all invited to kindly attend this and have a good time in Bangalore. The submission deadline is 15th of August, 2023. Thank you so much.
Yeah, there's a question.
Thanks for your excellent presentation. I have three questions. So have you considered to look into climate data or weather data, especially rain? Because I have experimented clear-cut detection using Sentinel-1 data, and I have seen some low accuracies because of the rain conditions.
Yes. So that's a good question, and we are actually currently doing that. So we are trying to use, see if we can use GPM datasets and also soil moisture datasets, because we are seeing that especially at C band, there are a lot of issues with rainfall, and then those patterns we are not capturing in cumulative sums of change, or they result in false positives. Also, we have seen impact of flooding. So whenever there is flood in the Kalimantan forest, the double bounce increases, and so suddenly there seems to be a reverse change that happens. And so in those cases, if there is a logging activity that has happened almost in the same time frame, we might lose out on those data sets. So those are currently being investigated.
And second question is that you didn't mention about topographic changes, because I think the gamma knot backscatter works much better than sigma knot if you have very much differences.
Yes, so I think I forgot to mention.
Did you use the gamma knot or sigma
Yes, I think I forgot to put that in the slide. It was all registered to gamma knot. And for Haldwani, the topography is very flat, so there the topography did not impact much, but we did not check it for Kalimantan.
Yeah, and thirdly, I have one suggestion for your cumulative sum change method. Because I have also proved that the 6-day or 12-day repeat path covariance works much better than gamma knot.
Okay.
I think if you can add that plugin to your
We'll try that, definitely. Thanks.
Thank you.
Armando.
Hello. Thank you. Very interesting presentation. I really like the use of cumulative sums. Very cool. The question is related to the selection of the reference, because this can be quite important when you have phenology. And also if you could say a little bit more which type of statistical test, or how do you do the training for setting then the threshold?
Threshold in the cumulative sums, or?
The cumulative sum, yeah.
Yeah, so right now we did not use any statistics, but we were just experimenting with setting the change point significance threshold. So right now 0.1 worked better for us, but we have to experiment more to see if it's a one-off chance or we need a better statistics for that.
So you do a change point analysis?
Yes.
I see. What about reference?
For the reference data set?
No, the reference for calculating the difference.
Yeah, we are only removing the first acquisition to use as a reference, and then we are taking the rest of the time series and computing the residual means from that.
Don't you see divergences due to phenology?
Yes, so we tried to, we have not yet completely understood how to remove that. We have tried to get a scene mean and remove the scene mean of the forested areas from each pixel.
Okay.
So that kind of removes, but so that resulted in some accuracy improvement, but I think there is still more scope to analyze it further.
Maybe we can have a chat. Yeah. Very good, thank you.
Hi, congrats for the presentation, very interesting. I will have two questions. One question is on your answer, right? Right now you said that you have seen an increase on the double bounce on flooded forests in Kalimantan area. You were talking about C-band, that was in C-band
Yes.
or L-band?
C-band.
You saw that?
C-band,
okay,
yeah.
That's
That
curious.
was probably because, so it's only for a few areas which probably had experienced some logging before, and then there was flood, because the river that flows, it has a tendency to overflow and then go back to its channel. So probably that's what we saw.
Okay, so it was a thinned forest maybe?
Yeah,
or, degraded forest.
Near the river areas which have a more probably degradation, so there is thinner forest areas there.
Okay, and I would like to have your opinion on the cumulative sums methodology as a warning methodology. I mean, what's the delay of detection using this algorithm?
So right now it's because only after the acquisition we have taken it, and so we have to use a time series, so there is a long delay. So it cannot be an immediate warning. We have to probably use bitemporal data sets for that to immediately see between two scenes, because here we need at least an year's worth of data to get the deforestation.
So you will say years, maybe?
1 year.
1 year, okay.
Because for at least for Sentinel, 28 scenes we could capture in 1 year, and so from that we could get the data. But we have not tested if at 10 scenes also we can get a similar accuracy.
Okay, thank you.
Okay. Given the time, we should continue the discussion on the Padlet and at the coffee break, which starts now, and we resume at 11:10. So thank you very much. There's Klaus. Wait a moment.
I have to make a short announcement. We are splitting now. We have two sessions. The agricultural session will be here, agricultural applications, and then the biomass validation and carbon modeling session will be in the small room in the back. For those who are in the small room in the back, please bring your presentation to the desk here, to Sabrina, and she will upload it. So it will not be uploaded in the room, it will be uploaded by Sabrina. Thank you.
Thanks a lot to the presenters and to everyone. Thank you.
Hello, the session is about to start. You are pleased to come back to the session. Thank you.
Hello, everybody. I'm Elise Collin from Onera, and I'm pleased to be here to chair this session with Armando Marino from the University of Stirling. We have 5 interesting presentations in this session on agricultural applications, and I'm pleased to welcome the first speaker, Jiao Xiangfeng.
Good morning, everyone. I'm Xianfeng Jiao from Agriculture Agri-Food Canada. Today, I'm going to present our research project, monitoring crop harvest and tillage using Sentinel-1 coherent change detection and polarimetric parameters. As we all know, SAR imagery has been using for crop monitoring for many years. There is an increasing need for continuous monitoring crop condition and management activities like seeding, harvest, and tillage. So we manage agriculture field from snow off to snow on, the entire life cycle of crop production. So information on crop tillage and harvest is a key for evaluate environment footprint, like a carbon footprint, resulted from crop production. Yeah, we have a study site in Russell area. That's an agricultural area in East Ontario, Canada. So the corn and soybean are major crops. And typically, the field will seed in late May and harvest in October. So every year, early October to late November is an active period for harvest and tillage. After late November, snow covers the field. In 2022, we have 2 passes, Sentinel-1 IW mode, dual-pol VVVH, single-look complex data. All study sites located in the overlap area, so that will increase our acquisitions. We conduct roadside windshield survey. That's, we start from August 26th last year, and we revisit the field coincident with the Sentinel-1 acquisition. We observed crop harvest, field tillage, manure application. We also visually assess soil moisture status in the field, like wet, dry, or moist. Before we use the Sentinel-1 SAR imagery, we check the weather station. We found that more frequently heavy rain events occurred during the acquisition days from pass 33. So we removed that image from that pass. this study only focused on the image from path 106. We download data from Alaska satellite facility and calculate PolInSAR coherence with SNAP. As we all know, Sentinel-1 SFC data has phase preserved. Other than backscatters, we're looking for additional information from phase. So we calculate covariance matrix C2, 2x2 covariance matrix with SNAP, and extract polarimetric parameters with PolSAR Pro. I show the results from PolSAR Pro. Before we use the PolSAR Pro, we only have a MATLAB code to verify we have correct parameters extract from PolSAR Pro. The first of all, we extract backscatters, VVVH, and span, that's the total backscatters. We also calculate stock parameters, 4 stock parameters, and a few polarimetric parameters can calculate from stock vectors. We also apply the entropy and alpha decomposition. This method, developed by Jean-Claude, can apply to dual-pole linear polarization. We also calculate the Shannon entropy. So over that study area, we have a corn and soybean in the field. So we analyze the corn and soybean separately and developed a crop-specific identification model. First, we plot the temporary change for all polarimetric subparameters we extract. These 3 graphs shows the temporary change for backscatter, VVVH, and span. These 4 shows the stock parameters, 4 stock parameters here. The first 2 shows the agent value L1, L2 from covariance C2 matrix, and the last one is the Shannon entropy. From this temporal graph, we do see the seasonal variation from these parameters. We see the value increase. So we see the value increase with the crop canopy developed and decrease as crop senesces. So during the harvest period, like late September, the value remained low. But we see here the acquisition from October 18th is odd. So we acknowledge that there is a few soil moisture affect that acquisition, but we only have the image every 12 days. So for this analysis, I did not remove that data, like October 18th data, but this data do affect our accuracy. We'll show later. Yeah. We developed a logical model to identify the harvest activities. So we want to keep the model as simple as possible and easy to implement for operational purpose. So I use the second graph as example to explain that logical model. So the second graph shows all soybean field harvest. So harvest between September 24th to October 6th. So we see the span value on the October 6th is really relatively low, And if we compare that span value to the acquisition previous acquisition before, we see the significant drop. So based on that relationship, we developed that logical model. So because of the data on October 18th, that's abnormal data we did not remove from the acquisition, from that analysis. We only get 70% of soybean field harvest detect from that logical model. We also tried channel entropy, use the similar logical model. So the same, we got 70% identification accuracy. After harvest, farmer will till their field. So here shows the INSAR coherence, we call it CCT coherence, change over time. For example, the first graph, we see that's all soybean field harvest between September 24th to October 6th. So that from here, the field will harvest. And if we see purple line, that's field tilled and harvest at the same time. So we see the coherence drop significantly, the all coherence value below 0.2. And the right line shows the fields tilled between October 6th to October 18th. So we see the coherence value drop below 0.2 again. The green line shows the soybean field harvest between October 18th to October 30th. So again, we see the significant low coherence value. The green line here, that's soybean field not harvested yet until November 11th. Last year, before November 11th, snow covered field. So we do not have a further acquisition beyond November 11th. So to determine tillage, we consider two scenarios. If we know the harvest days, like we can identify the harvest using Polarimetric parameters. When we see coherence lower than 0.2, so we see 100% field, that's because tillage. But if we do not know the information about harvest, the situation becomes a little bit complicated. We need two image pairs to determine harvest. So we either compare the coherence with previous. So we either compare the coherence with the previous the acquisition before, if we see the drop, or we compare the coherence with acquisition after, if we see the significant increase. That means after tillage, the field conditions stay stable. So that's why the coherence up, going up. That's the two scenarios we considered right now. So for cornfield, we applied a similar analysis for soybean. So that's Polarimetric subparameters time series change over the cornfield. That's for stock vectors. That's for entropy, for agent value and channel entropy. for corn harvest identification, we try a little bit different logical model. We select a model from the beginning of the season, like June 20th. There's almost a bare soil in the field. So we set this day's acquisition as a benchmark and compare the acquisition with that benchmark. If we see the span value lower than that benchmark, and then we also compare I use the second graph like example. We also compare the span value with the acquisition before. If we see significant drop, so we identify that harvest occurred. Because there is no harvest event occurred around October 18th, so that's image abnormal, not affect our identification accuracy. We got 85% of cornfield were identified as harvest. We also tried a similar logical model for Shannon entropy. We have a 78% identification accuracy. So cornfield were tilled much later than soybean field. The most field tilled after October 25. And November 11th, we have snow covered. So I only have 2 pairs of coherent value, so do not have enough image pair to determine the crop tillage this year. The purpose of this object, that's for operational, we want to generate a harvest and a tillage map. So to do so, the first step, we need to identify all soybean and corn field over this study area. So Agriculture and Agri-Food Canada release the annual crop inventory every year. So I use that data, identify the corn and soybean field over the study area. And that's time series polarimetric subparameters for all soybean field. That's cornfield. So we applied a logical model to generate a harvest map using polarimetric parameters and the tillage map using a coherent change detection. That's all preliminary results from the data last year, 2022. We will continue to collect ground data this fall to improve and validate that methodology. Thank you for your attention.
Thank you very much. Is there any question in the audience?
Thank you for your presentation. You used some values using this span to detect the harvesting dates. So my first question is how these values are decided, and are they not ambiguous to some other phenological stage of the crop?
So the first question, so we plot all temporary change for all parameters we extract. So some parameters we do not see any seasonal variation, so we do not use that parameters for now. I do not say there is no information from that parameters, but we do not use that for now. So we see the span and Shannon entropy is the most significant change over time. So we select that one. But I'm sorry, what's the second question?
Those values, what you use to determine the harvesting dates, those values, are they not ambiguous to some other phenological stage of the crop? Confusing or like, matching with some other phenological stage of the crop?
Phenological state, you mean the crop phenological state?
Yes.
So we do have a project to estimate phenology, use as a polarimetric parameters. But this project, we just use as parameters to monitor harvest and tillage. So no crop phenology considered here. But we do see, if we see the temporary change, we do see the values varies from the different crop phenology.
Okay, thank you.
Thank you for your presentation. The last slide that you showed the classification of tillage and harvest, you didn't explain well how did you use those parameters or time series profiles for this classification. I think you mentioned that you used logistic regression, but
Yeah.
how did you train your model?
Yeah, so that's the first year we only have 1 year data, right? So we would call that as a
did you use the time series data for this classification?
I think this is time series change detection.
No, the input to this model, the logistic regression, was this the time series of these parameters, right?
No, I just used the logical model and showed here. But I said that's our preliminary results for this project. So how to generate that map, we're still working on the methodology. So we will consider, so I do see a few interesting presentations from that conference. We will consider use the 1 more year data to improve that map generation.
Okay, thank you.
Thank you.
Thank you. Because we do not have so much time for all questions, please do not forget to comment on the Padlets if you have other comments or recommendations, because it's a very specific applications agricultural field, so do not hesitate to add some comments. Thank you.
I may add something. Oh, sorry, really. Coming back on what Vahid was saying. So do you know what are the agricultural practices in this place? So do they always soybean in the same fields? Because in that case, you could go the year before and look at the trends and this already to...
So if I understand the question correctly, so the equation here, the T is time and I for each soybean field. So we will say each field have its own story. So we do not set hard, like absolute value for that logical model. So we compare the field by itself.
Okay, so you cannot say the same guy, same farmer grows always in the same way. You don't have this assumption.
Yeah, so exactly we compare the acquisitions with same field.
Thank you. So we can now go to, first of all, I'm Armando Marino from the University of Stirling, and it's really a pleasure to be chairing this session. It's also a pleasure to see that so many people stayed here and they didn't go in the other room, so the competitors of our session. So thanks for staying here. As Elisei, I would like again to ask you please to use Padlet for your recommendation, ask questions live, or you can post them on the Padlet. So I would like, without further ado, like to introduce the second paper, which is Polarimetric Processing of and Analysis of Sentinel-1 time series for statewide crop monitoring in Victoria, from Shuo Shengshu, hope I pronounced it well, from CSIO, Australia.
Yes, thanks, Armando. Good morning. Today I'd like to talk about how we use the Sentinel-1 time series, use the polarimetric analysis for crop monitoring in a large area. So, So for a large-scale crop monitoring, I think these are the main challenges. We say the large scale is not within a couple of things or. Okay, that's great. It's not within a few Sentinel-1 things. We are talking about 100 things, something like that. The routine observations without weather restriction is a key, and also genius or optimize the data process, and also sufficient ground sampling data is always very challenging, and also robust classifier for group classification. And also other things about accurate group map as early as possible during the growing season, because they are very important for the agribusiness. They are keen to have the accurate group map as early as possible. Okay, let's see how we answer these questions. Here is my talk's content about the wheel build in Australia and also Sentinel-1 coverage. And also talk about the polarimetric process and analysis of Sentinel-1. I WMO the dual pole data by the slab, and also group type classification use the dual pole products of Sentinel-1 time series, large scale group type mapping through classification propagation. And this is Australia. We have more than 300 Sentinel-1 things to cover the whole country, but those area are mainly the wheel build. Australia is the one of major grain producer and also the export. So here have the all Sentinel-1 things footprint for the wheel build from the east coast to the western Australia, WA. Here are our some the Sentinel-1 SLC data process workflow. They are quite standard, some process workflow. We initially use not overflows for the data process purposes, but later on, we have improved some of the workflows. This is, we do the process for normalize the backscatters and also polarimetric decomposition products. We use the GRD for the backscatter, normalize the backscatter generation, use this workflow. Especially I use some the thermal noise removal and also terrain flatten. Because the Australia is, the agriculture zone is normally quite flat, but still some is not totally flat. We still need to do some terrain flatten to remove the variation of the red matrix. Also, we are very keen to use the dual pole for some polarimetric component for how we see the polarimetric could improve the group type classification. This is the Sheehan cloud dual pole decomposition algorithm, which was present first in the PolInSAR 2007. So when the dual pole two channels receive incoherent, the coherent matrix can always decomposition as the dual pole channels, the eigenvectors decomposition like this. So based on this concept, we have improved the SLC data process with significant same noise removal. This work was independent of the Marcelo reference paper from the Juan Lopez Sanchez, the team from Spain. So the main part of this work, we process the whole thing because we use a supercomputer to do the large volume data process. So we are able to process the whole thing at once. So they separate each of the subswaths into the emission part and the intensity part. We use same noise for the amplitude part, and then to do some standard, the calibration, the top star deposit and merge, and combine the phase information with the noise removed, the amplitude, and the construct to the coherence matrix, and then combine three subswaths merged together as a whole thing for the further decomposition process and also smooth filtering and Terran geometric correction. And then as analysis-ready data for each of the things. Now we have looked about the new process compared with the previous one. So this is with the dual pole entropy with the noise before. This is after noise removal. We can see significantly improve about the process. The dual pole entropy alpha decomposition for improved group type discrimination. So let's see how we use the intensity, the VH and the VV, and also we incorporate the entropy alpha and anisotropy, how they will improve to the group classification. For example, this is the 1 day of Sentinel-1 acquired during the middle of the growing season. Australia crop growing, the sowing is something in after the autumn. In May, waiting the rain coming, they will growing May different from the June and July, start growing, harvest around the November, December. But we are look at the data acquired in September during the middle of the growing season. So here, the A show one patch of we only use the VH and the VV. So you see the classification map. The B, we use the VV plus VH and the plus decomposition parameters. We can see significant improvement. But if we compare, use the time series, we can see more clear the classification result for this patch. This is a large one, more complicated thing. We still see the significant improve if we add the decomposition products to the group map, even with the single observation date. Now we have some analysis about this the data set. Here is use some is called the colonic variance analysis. They use the colonic root. When you have the data set, they calculate the colonic root and see different class. How about the separation about the different class, the colonic root? So if we only use VH, the separation score is about 1.2. If we use VV, it's similar. But if we combine dual pole, intensity is 1.8 improve. But if we use only the decomposition product separately, they are some equal to the intensity only. But if we combine both, the separation score is much larger. This is give evidence how the polarimetric analysis will improve classification accuracy. So now we look at the more large area for the Victoria State, use the SN1 time series. So we look at the data acquired from April until December. So we look at, first we look at as many as possible the data set to find the features from data set. So all the data set has been pre-processed as used above the workflows, and then the random forest classifier or apply to each of the data state with corresponding the training data set for group map. So let's give you an example about how the length of the time series help to improve the classification accuracies. For example, this is acquired from April to July, very beginning of the growing season, August, September, middle of the growing season, October, November to December. So the data set length is about 5 days, 7, 9, up to 15. So you see, within the length increase, the group map accuracy is increased. So now, also, we know they're very difficult to discriminate the body and weight. They are very similar in terms of the shape and also signatures, but using the time series, we are able to discriminate the body and weight. Here show only the body and weight. So very clear discrimination. Especially when you have the noise removal and also properly the spike filtering, the particle boundary will be reserved. That will significantly help your discrimination of the particles. So now we have the similar the CVN analysis. We see how about the separation score with the different lengths of the time series. So when the length data set increase, the separation scores increase. So now we have a lot of question regarding the ground training data sampling. So here is the main ZR5 orbit for the Victorian state. We have a major ground training data collect within this area. This is the intensive agriculture zone. But we didn't have ground training data for the other orbit. We cannot mosaic all the the things together and do the classification once, use the same, because they come from the different time and spatial information. So they are not make quite sense to do this kind of classification. So now, how we do this classification? For example, we use the training data for this area. We could do the classification for this orbit, 1, orbit 2, and then we use the classification map, create a training data set for over this overlap area, because in this region, the overlap area is about 80 kilometers in terms of this direction, 80 kilometers. Give you enlarged buffer to create a new training data set and then train the data collect around this orbit. That's what we call the classification propagation. And also when you use the random forest classifier, they provide not only the group map for the whole thing, they also provide the probability for each class in that pixels. So we use a certain threshold value to select the new training site. For example, we use something about 50% up to 90% within the area and create a new training site for next orbit. And then we propagation this classifier one orbit by another. So in this case, we are able to make the large area group map possible using limited ground training data set. So this is, we just talk about how we use the training data set propagation. This is quite large the buffer for generating a new data training set. So this is from orbit, Victoria orbit 2. This is the relative orbit of Sentinel-1. So we do this and get the classification for the number 3 and the number 4 and number 5. So after all those, the class map for each orbit has been generated, then we mosaic together to form a statewide group map. Within the with the Atlanta user mask and keep only the group zone as the group map in this view. This summary. So agribusinesses are keen to have group map information with reasonable accuracy. Absolutely, more accuracy is better, but they are keen to have this map as early as possible. So we try to provide this information at the middle of growing season or as early as possible. And also large-scale group map from the wheel built in Victoria in 2016 growing season. And we use 25-meter pixel spacing for all those processes. Especially, Polarimetric analysis of dual-pole Sentinel-1 data provide additional information for better group classification, area estimate, and group growing state monitoring. And the classification with variance of time series, I compare, and the longer time series shows better classification accuracy. But early type prediction with reasonable accuracy is feasible. So especially classification propagation is quite useful for quite large area scale group mapping in case of lack of ground training data. Actually, national group mapping has been rolling out for all the wheel building Australia since 2007, but unfortunately, until 2021. So this is the Sentinel-1 coverage for Australia, all descending with all 21 the orbit. This is since the beginning of December 2016, but yeah. This is a mosaic for the whole the country, over 300 products. This is an example. We use something data about 5 days and 8 days acquired in between the June and September. We will see, provide the first group map in August, get group map, something like this. We provide a lot of products. In September, we will see increase the group map. This is current Sentinel coverage for Australia. This some main impact low group map in the Western Australia and also South Australia from 2022. And we have monthly statewide land monitoring in WA, but now shrunk to only 1/5 on this bit from 2022. So we are really looking for the Sentinel-1C launched. That's all my presentation. I also like to post this postdoc position to the SAR PhD students. So that will start from early next year. The information will be posted online next month from SARO's the job website or the PolInSAR group at LinkedIn. Australia is a lovely country, so you will enjoy the career development opportunities and good working and life balance and a safe and a very livable environment. Thank you.
Thanks for the presentation, very interesting. I have a couple of questions, but first let's see if there's a question from the audience. Yes, please.
Thank you for the presentation, very impressive results. So I noticed that you got the best results when you use the VVVH polarization channel along with the cloud alpha parameters, entropy, anisotropy, and the alpha angles. So I was wondering, out of these set of parameters, what was the most important parameter that gave you the best result? Was it the cloud alpha or the anisotropy, the degree of polarization?
Yeah, apart from the intensity channel, VH and VV, the entropy and the alpha scatter angle are also very important. If we just saw for one date, actually, why we use the decomposition products, within certain lengths, up to 8 or up to 5 dates of the time series, the polarimetric component contribution with some significance, but after 8 days, they will saturated for longer the time series.
Okay, thank you.
Question, please?
Yeah, thanks for the presentation. Are you planning to do any validation against in situ data or something like that? Because that looked, from what I could understand, there's nothing like that.
Yeah, that's a good question. Unfortunately, this work was just a trial. We have not done the validation for this part of work. So I would think to the next step, we may propagation back to see how the accurate, if we propagation back to the orbital number 2 to see how cross correlation between the original one with the new. But for the national scale rolling out, they have different the validation.
So you don't have access to information about what was planted where and when?
Yeah, they are different calendar reports.
Okay, thank you.
Question, Aid, please.
Thank you for your presentation. So you presented classification accuracies with different number of images over time. So have you, because it involves a lot of computations and it's very expensive in terms of computational time, have you looked into your overall accuracies with the number of images used? And then maybe after some time, or maybe you've used 5 number of images is good enough. You don't need to train with 10 images because it needs a lot of time to process this. And just maybe it just converts enough, and then you don't need to use 10 images. If you use the 5 images, you get enough accuracy.
That's right. That's right. That's right. That's why we test the 15 days just for graph information exported to see what's the best optimize the length of the time series. For the, I just mentioned for the national Polarimetry, the products, we use the 5 days to 8 days. And then provide the better accuracy mark and also as early as possible the reporting date.
You have time now for a very quick one. Otherwise, I keep my question for later and we go to the next. Thanks again for the presentation.
So we will move to the next presentation, a novel crop classification method based on PPF SVM classifier with time series alignment kernel from dual polarization SAR datasets. And it will be given by Gao Han.
Good morning, dear chairs and colleagues. Sorry for that. My Chinese colleague cannot be here because his visa issues, so he just sent me a recorded video to present his presentations, so I hope you could kind of understand that. And please enjoy the video. Thank you.
Dear committee, dear Professor Alice Colin, good morning. I'm Gao Han from China University of Petroleum. I'm so sorry that I can't report on site due to visa issues. For easy understanding, I have prepared a video to describe my report. In this report, I will introduce a novel crop classification method with dual polarization SAR datasets, which use a PPF SVM classifier with time series alignment kernel. Here is the contents, including 5 parts. Firstly, we introduce the introduction. As well known, the crop classification and mapping is important for agriculture. It is an engine for protecting food safety. With remote sensing technology, there are also many products and applications. For example, the word cover product by ESA, the Cropscape by USDA, the Globeland 30, the China Car 28 by some professors. They are promoting the rapid development of crop remote sensing technology. Among three common means for monitoring crops compared with manual investigation, the remote sensing technology can faster monitoring crops in large-scale parcels. Furthermore, the radar remote sensing technology is an active remote sensing platform and uses the microwave signals. It has the advantage of all daylight and all weather conditions, so it can continuously monitor crop growth. So let's see this figure. This figure demonstrates the advantage of PolSAR technology. The microwave signal can penetrate the crop canopy and then obtains the echo signal in canopy, stalk, and ground. So the PolSAR features can describe the structure and permittivity information, which is useful to describe the crop growth. Then, for the crop classification, we can say that the crop is a kind of time-varying object. Single-date data is hard to discriminate different types. For example, for the corn and the sugarcane, on June, the structures are similar, so that if we want to get the accurate crop classification results, we must use the time series PolSAR data. Now, there have many PolSAR satellites. This figure lists some main PolSAR satellites launched from 2000 to 2023 year. We can see there are more joint observation means and shorter revisit interval. It proves the PolSAR satellites can provide rich data for crop research. As for the crop classification methods with time series PolSAR data, we can divide it into two categories according to the utilization of time series features. The first kind of methods look at the multi-temporal information as a stack of features. They use a machine learning algorithm to discrimination, such as the maximum likelihood, decision tree, and SVM algorithms, but it has some drawbacks. These methods have not applied the dynamical characteristics, and the classification ability is limited. And our method is about the improvement of this kind of method. Then the second kind of methods are developing rapidly, which use phonological knowledge or time-varying features. The phonological information can be applied in the improvement with many ways, but it also has disadvantages of high cost of sample collection and ignores the influence of phonological unalignment. Now, for the phonological unalignment, the classification with time series alignment algorithm have been developed rapidly. It looks the time series features as a curves and extracts curve similarity to achieve classification. So what is the phonology unalignment? This is it is some time series unalignment caused by agri-climatic conditions and agricultural practices. It can introduce many classification errors. For this phenomenon, use the time series alignment algorithm, and the dynamic time wrapping alignment is a typical algorithm. It can search optimal paths to match different curves. It is some scheme. Then the traditional classification scheme is nearest neighbor classification with time series element similarity. We use this similarity into the nearest neighbor classifier to achieve the result. But this method has some problems. The first problem is the DTW element is a point-to-point matching, so it's leading to leading some unreliable alignments. It also can be defined by singularities behaviors. It means one point to multi-point. And the second problem is the NN classifier occupies in a dequant generalization performance. So that we propose a novel classification. It has two innovations. In the innovation one, we replace the DTW element with the TW shaped DTW element. Then in the innovation two, we use the PPF SVM classifier to do. So the combination of this is applied in the kernel function and achieve a novel method. Then we introduce the methodology. The first innovation is about the DW-shaped DTW element. This is the formula of it. It has two improvements. The first improvement is about point-to-point matching, and it can be replaced with shape descriptor. So we apply the shape descriptors, then can use the neighbor information of a subsequence to improve the alignment accuracy. The second improvement of it about we add the time weight in it, so we can use the temporal constraint to avoid some unreasonable alignment. And then we can, based on the TW-shaped DTW alignment and extract two kinds of similarity, including shape similarity and feature similarity as our features. Then in second innovation, we use PPF as SVM classifier. So the first question is how to combine the time series similarity and SVM classifier. Because if we use the traditional sort, use the similarity to replace the Euclidean distance in kernel function directly, then the kernel matrix is not positive. So we must solve it. We use the PPF SVM classifier. The dual similarity of features can be constructed. Then the proximity vector and the proximity matrix can be generated. So we can achieve the positive kernel matrix byproduct. This is a total technology scheme. Okay, let's see the study error and data. We use the study error in Gansu province of China, and this is, there have two regions to do the experiment, and we use 22 Sentinel-1 dataset in 2018 and 2019. This is about the crop types. There are 7 types, and this is about their phonological distribution. This is training samples and the testing samples. Okay, this is the time-varying feature curves. We can see different crop types have their own traits. So it can prove the feature curve can achieve the classification of crop types, and we can see our feature curve can prove and demonstrates the leaf growth and the stem allocation. So the fourth part is the results and the discussions. this is our classification results. We can achieve the results in 2 years more than 90%. And this is about the crop rotation from 2 years. We can see the rotation weight to rip and annual to weight or cone. This is consistent with local crop rotation. And this is comparison with our method with and other classification methods. This is overall accuracy. And our accuracy is highest. This is the classification error maps. This is typical cases. We can say, considering the time series alignment, the parcel can be correctly discriminated as ANIA. And considering the time series alignment and PPFSM classifier, the parcel can be correctly discriminated as which. So this is robustness. We can say under a different number of training samples, our method can retain the highest accuracy. And this is a comparison with different time series alignment. And our TW shape DTW can achieve the highest accuracy. And we discuss the influence of various features on classification. All features, the combination of all features can obtain the highest. And we discuss the sensitivity of classification methods to the number of features. We can see our method can obtain the highest accuracy under different numbers of features. And for the different intercorrelation of features, our method's sensitivity to the intercorrelation is lower than SVM method, and our accuracy are higher than SVM. So the final part is about conclusion. We propose a novel crop classification method. This method established a bridge connecting time series, PolSAR data, and crop classification, and successfully combines the time series alignment and the machine learning algorithm to improve classification ability. Compared with different classification methods, the PolInSAR method are the best, and it can be used in the large-scale crop type mapping. Okay, that's all. Thanks for the attention. If you are interested in our work and the corresponding course, welcome to contact me. And the other experimental details can be seen in following articles. Thank you. Dear committee.
So I guess it will be difficult to ask questions directly to the author remotely. So I don't know if there is any comment, perhaps, to discuss together or. Something in the back? No. If no, we will move to the next presentation.
So it's my pleasure to introduce next speaker, Lorenzo Papale from Tor Vergata room. The title is Sensitivity of Different Scattering Mechanisms to Soil Moisture and Vegetation over Cornfields in Argentina.
So thank you for the introduction, and good morning, everyone. Today I'm going to present this joint work with the Sapienza University of Rome and CONAE. And before starting, I want to thank Giovanni Anconitano, which is the first author of this work, but also Olena Sarabakas, C. Mokrane-Siad, and Professor Nazareno Pierdicca, sorry, from Sapienza University of Rome, Professor Guerriero from Tor Vergata University of Rome, and Mario Acuna from CONAE. So, before starting, I want to highlight what are the objectives of our research. So the first one is to evaluate the capability of full pole radar system in highlighting the sensitivity to soil moisture and also to vegetation variations by analyzing time series of full pole SAOCOM data over agricultural areas located in Argentina. And also, we are going to apply 4 polarimetric SAR decompositions, the Freeman-Darden, the Van Zyl, the generalized Freeman-Darden, and the Yamaguchi one. So we apply these polarimetric decompositions to covariance matrices obtained from the SAOCOM time series to identify the canonical scattering mechanisms, also surface, double bounce, and volume scattering. And at the end, we compare the scattering contributions from the polarimetric decomposition with the one obtained with an electromagnetic model developed at Tor Vergata University. So, starting from the electromagnetic model, the Tor Vergata model is based on radiative transfer theory applied to discrete scatters with simple shapes. And these scatters have particular absorbing and scattering properties, so that the vegetation is modeled as an ensemble of simple scatterers with simple geometries such as disks and cylinders to model leaves and stalks. And this model takes as input some sensor configuration parameters such as the signal frequency, the incidence angle, and the polarization, some soil parameters such as the soil moisture and soil roughness, and the vegetation parameters such as the plant height, but also the geometrical and absorbing scattering properties of the scatterers. So the vegetation layer is divided in thin sublayers, and the matrix doubling algorithm is applied to model the interactions of any order in terms of attenuation and scattering mechanism across all the sublayers, and then between the 3 main layers, which are the soil, which is modeled with the advanced integral equation model, the stalks layer, and the vegetation canopy layer. Concerning the polarimetric decomposition, as I mentioned before, we selected these 4 polarimetric decompositions. Some of them are model-based, while we have also decomposition based on agent values and agent vectors and hybrid ones. But in any case, we use the covariance matrix as a combination of the scattering mechanism to obtain the powers. So not only the total power, but the components. So the power related to the surface, the double bounce, and the volume. These slides is just to summarize as a workflow what we have done. So we collected the input parameters for the electromagnetic model to obtain the simulated surface, double bounce, and volume scattering contributions. And at the same time, we processed SAOCOM time series and applied polarimetric decomposition to obtain the same contributions. And at the end, we performed a comparison between the Tor Vergata model and the results of the polarimetric decompositions. Now, just have a brief introduction to the area of interest and the ND dataset. So we have a time series of SAOCOM single-look complex images acquired between October 2019 and February 2020. And we selected in that area 5 cornfields, in particular in the Monte Buey test site in the Cordoba province. And in the same period, a field campaign was conducted by CONAE, measuring different parameters such as soil moisture, plant height, and growth stage. And also we introduced the NDVI, deriving it from Sentinel-2 acquisitions and by linearly interpolating into the SAOCOM acquisition dates to have an indicator of the vegetation development. So at the end, we have 9 images composing our time series. So, as I mentioned, the Tor Vergata model needs some parameters as input. One of these, one of them is the plant height. But unfortunately, in the in situ measurement, we had considerable missing values, so we had to derive these parameters. So firstly, we derived with a sigmoid function fitting the growth stage starting from the days from sowing, and then we found the plant height as a function of the growth stage. At the same time, we also the soil roughness, it's an input parameter of our model. So since it has not been measured during the in-field campaign, we derived the optimal surface roughness by minimizing the error between simulated and the SAOCOM data by varying every time the soil roughness ranges. And as you can see, the magenta line is the one related to field B23. We have some problem with this field since the minimum root mean square error is about 4 dBs. And it can be addressable to the sowing direction, which is different to all the other fields. Then we integrated also the soil moisture measurements, the one that were available for that fields in that 9 dates, to obtain a point-by-point comparison between the simulated and the SAOCOM data. So as you can see, the simulated data followed basically the same dynamic range and the same trend of the SAOCOM data, and the lowest backscattering values are associated to bare soils in cross-polarization, while the highest values are related to well-developed fields in copolarized polarization. And also in this case, the highest root mean square error is obtained for field B23. And in general, we can say that the model slightly underestimates the backscatter values. So we computed not only the root mean square error, but also the unbiased one to obtain a result of 2.15 dBs. And here in this slide, we have the temporal evolution of the contributions provided by the polarimetric decompositions. In the first line, we have also represented the values of soil moisture when measured. And in the second line, we have the values of NDVI provided by Sentinel-2 acquisitions. And in the first case, we cannot observe a direct correlation, especially for the surface components with respect to the soil moisture, also for a lack of data in soil moisture measurements. But if we look at the second row, so the NDVI values, we can observe that the volume component and the double bounce component follow the same trend of the NDVI. In this slide, we have a comparison in terms of powers between the contributions obtained with the model and the contributions obtained with the polarimetric decompositions. And as we can see, there is the Tor Vergata model and the polarimetric decomposition. There is a good agreement between them when the fields are well developed, while at least for double bounce component and volume component, while for surface scattering we have the opposite. So we have, except for a bias, a good agreement between the Tor-Vergata model and the polarimetric decomposition when the fields are not well developed. And concerning the soil moisture, again, we can say that there is not a direct correlation, since in most of the part of the scatter plots we have a mixture of high values and low values in soil moisture. So we applied also this comparison considering polarization by polarization, and this is the HH1, considering just 2 polarimetric decompositions out of 4. And we obtained that basically for the double bounce and volume scattering, we have the same behavior as before when considering powers and not the single polarization. But we have for surface scattering that in this case, in HH polarization, we have that the points are closer to the one-to-one line. And this is the VV polarization. Basically, the behavior is the same of HH. Besides, in the surface scattering, we have that for well-developed fields, the model, the Tor-Vergata model, attenuates a little bit if compared to the polarimetric decomposition. Basically, not so little bit, it's around 10 dBs. So we have to understand, basically it can be addressable to the way the model represents the stalks of the corn plant. And this is the HV polarization. From a theoretical point of view, the polarimetric decompositions we have applied provides not a number for cross-polarized channel for surface and double bounce, and but on the contrary, the Tor-Vergata model provides significant values. And if we observe the volume components, we have that the Tor-Vergata model and the polarimetric decomposition are in good agreement, except for a bias. So to conclude, concerning the surface scattering, we see that the Tor-Vergata model and the polarimetric decomposition are in a very good agreement where the plant is not well developed. And on the other hand, the volume and the double bounce components are in good agreement when the fields are well developed. And it can be observed that the Tor-Vergata model provides a higher attenuation, especially in VV polarization, of course, when the vegetation grows. And on the other hand, the polarimetric decomposition don't provide a contribution in the cross-polarization channel for double bounce scattering mechanism. And concerning future works, we intend to apply other polarimetric decompositions on SACOM data to perform a robust comparison between the decompositions. And also, we want to use a semi-empirical model, such as the water cloud model, to simulate the different scattering mechanism. And also, we want to try to integrate the information provided by the Tor-Vergata model, especially the one concerning the double bounce in the water cloud model. And we want to apply also polarimetric decomposition to simulated covariance matrices. to observe the difference between the results of this procedure and the components provided directly by the model. And from a general perspective, the objective is to deal with sensitivity to soil moisture. So these are our preliminary results, but the direction is to assess the sensitivity of these contributions to soil moisture. This was my last slide, so thank you for your attention.
Thanks, that was very interesting. And I'm sure there will be a question from the audience. Yes, please.
Morning, thank you for the presentation. I was wondering, how do you assess the distribution of vegetation through the canopy and the plant water content?
You mean in the model?
Yes.
The distribution is done by fitting in-field campaigns, and in this case, the model was calibrated on Argentinian maize, but not for this campaign. Another campaign conducted by CONAE in the same area. And that campaign was more complete, so we had a lot of values concerning growth stage and the number of leaves, the dimension of leaves, and also the properties of the stalks. So the model was calibrated on that corn fields that we assume that are very similar to the one we have dealt in this study.
Thank you.
Thank you.
Other questions?
You mentioned that you saw higher attenuation in the VV as the plant grew. Do you have an explanation for that?
For the attenuation in VV polarization?
Yeah.
Yes, basically the model takes as input all the, as I said, the absorbing, scattering, but also geometrical properties and orientation properties of each scatterer. So we assume that the orientation of the stalks and also their dimension can contribute more in VV polarization than in the other polarization, so that the attenuation is more visible in that polarization.
So did you examine if this could be an effect of double bounce from the stalks?
It can be, yes, it can be related to the double bounce effect, of course. And we are using SACOM images, but and also the simulated data are at L band. And we saw that for these incidence angle intervals and for this frequency of the signal, we have a strong contribution of the double bounce effect for this kind of crop. So basically, it can be strictly related to the double bounce effect, interacting, of course, with the stalks of the plants.
Thanks.
Time for more questions. I have one, which may sound a little bit weird. At the start, you were doing this comparison between your radiative transfer model, so say quite agnostic, say on type of model you use, you fit, to technique. It's almost model free. Yeah, with the decompositions, model-based decomposition, which has a very strict way of looking at the world. So a very strict way of models that they used. So what's the point of this decomposition? So why, if you are similar to, say, the Van Zyl, it's not necessarily a good thing. Because, you know, this is the way they see the world. You don't want to see the world that way. You want to see the world the way it is. So why did you do this comparison?
Basically, we are trying to, the final objective of this work is to provide from the electromagnetic model some information, some physics-based information to the actual observation of data. So at this preliminary stage, what we have done is to compare the different techniques. Of course, when we apply the Tor Vergata model, I show the scatter plot to assume that what we have simulated is very close to what has been observed by SAOCOM. But of course, to understand if these techniques are strictly correlated to the actual conditions of soil and vegetation, we have to perform more robust and complex sensitivity analysis on measured data in field campaign.
But this is okay. No, my point is that misagreement between you and, say, the Freeman Darden is not necessarily a bad thing.
No,
so
of course.
Don't take it as a bad thing.
Of course, in fact, we are trying to understand where, for instance, the model overestimates and the decomposition are underestimating. So we are trying to understand which is the one more close to the actual conditions.
Thank you.
Thank you for the question.
So we can possibly go to the next speaker.
Okay.
Thanks.
Thank you.
Thank you. So the last presentation, last but not least, will be given by Nathan Payou on temporal coherence of multi-temporal polarimetric SAR data with application to agricultural event detection using Sentinel-1 data.
Thank you, Elise, for the introduction. So hello, everybody. I'm Nathan, and nice to meet you. I'm an engineer at Capgemini, and I'm going to present you the last research we did in the scientific team. So for this work, I worked with Sandrine Daniel, who is a SAR expert like me, Susan Angeli, a data scientist, and Maxime Demazo, an agronomist. So I'm going to first explain you why we suddenly decide to study the currents for agricultural event detection. Then I'm going to explain the methodology, presenting the data set, the ground truth, and the new method we used for the study. And finally, I will present the first result we obtained. I will show you that why our new method is better than the classic temporal currents. I will show the first good result, but also the issue, because we encountered a lot of issue during our study. And therefore, I will conclude with the leftover and perspective. So the context. First, there is a need for the farmers to have a better control of their production. Therefore, being able to have better knowledge of the event when they happen would gladly help them. It will allow to have a better prediction by identifying the best farming practice. It would allow better monitoring of the state of field. For example, when the flowering happen, disease control or irrigation management. For now, we don't have this in France, but I'm sad that we have soon some irrigation management problem. But it can also help for the logistic, for example, when to know which silo the farmer have to use in function of which field have already been harvested. From a government perspective, it is needed for the new common agricultural policy. In short, now every country needs to perfectly know the state of the fields in this country when they are harvesting and everything else. The idea is to be able to give more easily and more precisely the subsidies. So it is an important part of our job because we want to help the government to do it. Another important thing for the government is the possibility to forecast and manage agricultural or environmental crises. If you have some fields who give less than what we were expected, you could have an agricultural crisis in a region. So linked to this need, there is a need of scalability. The actual method, for example, is France to know the state of a field, is to send an agent, a human, and he visit it. So we roughly managed to do like 5%, to cover 5% of the field actually in France, but we will need for the new policy to cover 100% of the fields. And obviously we can do it using human agent. It's why we want to use some satellite data. And we would like to provide to the farmer an easy-to-use method to allow them to more precisely control the field, the state, and to be able to communicate this information to other farmers. So at Capgemini, we already worked on this subject, but we only used optical data. And as you know, it doesn't work properly when there is cloudy days. There is quite a lot in France, and therefore we can't precisely date the eventment. We tried to use a bit the SAR currencies, but we had a problem because it was an area fields in C-band using Sentinel-1 data have low currents, and therefore we weren't really convinced by our method as we had low currencies. So now I'm going to present the data set and the ground truth. So the data set, we used some Sentinel-1 EW SLC data. I think that all of you know about it. It's data from summer 2022.
and we process them with SNAP. We calculated 7 covariances as we had 8 images, and we used a 15 by 3 window. So therefore, you can see that we have a huge spatial averaging. So it's first one of our problem, because sometimes we have very small fields, and you have to have a good spatial averaging, because you need a good estimation of your covariances, but therefore you encounter problem for small fields. So for all this field and all this data, we calculated different variables that we try to use to detect this eventment. Concerning our ground truth, it's a graphical parser register, so it's data which is provided by IGN, a French organization. And more precisely, for our study, we visited 63 fields over the nearly 200 fields that there is in our footprint. And this visit was done by a human agent for one date. It means that you have to understand that the agent came here in the end of August, and sometimes he says something like, okay, the flowering of the crop happened maybe 1 month before. So it's really difficult to have a precise controls. So to give you an idea, on the right, you can see an image of France. I highlighted the 3 most important cities, the capital, where we are here, Toulouse, and I'll let you guess from where I come, Bordeaux, the beautiful city. And you can see that the acquisition is really small compared to France. It means that to cover the whole France, you would have to do a lot of acquisition to process, and for every date if possible. I'm going now to present the new method we used. So I will briefly remember you what is the occurrences. So for monopolarization, we use two acquisition 1 and 2. We calculate the expectation value using the complex backscatter for the 2 images for one chosen polarization. You can see on the right an example of images. When there is a lot of changes, you have occurrences close to 0. When you have no changes, you have occurrences close to 1. It's why you can see in the images here, for example, it's a city. There is low change, so you have a bright area. When you use multiple polarization, so dual polarization in your case for Sentinel-1 data, you define a current scattering vector using the polarization. After that, you create 3 matrices. So the current matrix for one images and the other images, and the temporal PolInSAR matrix. After that, you obtain the Polarimetric interferometry covariances defined by this huge formula here. One important thing is that you can see we use 2 vectors, W1 and W2. They are unitary complex vectors. In fact, they are linked to the scattering mechanism. For example, if you choose for W1 and W2 1, 0, you will define the VV polarization. If you use 0, 1, you will define the VH polarization. And after that, you can mix it. Okay, so now I'm going to present the new method. So it's called reinterpreted temporal currents, who was represented in the paper cited below. So the idea is to divide the covariances in 2 terms. One is called row symmetrics. So it accounts for change under the equal scattering mechanism assumption. So I detailed the explanations that I gave. You can see some decoration we all know about. For example, the temporal decoration or the signal to noise decoration. And the one which is more interesting for us, it's the asymmetric part, which is defined below. And this part accounts for non-current changes between both images. And it explains in the paper that this row asymmetric low characterization of PolInSAR data for low current scenario. So it's exactly the case we are. It has also been demonstrated in this paper that if you want to maximize the row asymmetric, you just have to solve the eigenvalue problem which is indicated here. And therefore, you can use all the eigenvalue or the corresponding row asymmetric optimum. And using this value, you can better characterize your scene, and it's a best way to have a good coherence to study. Okay, so now I'm just going to quickly explain the difference between the two, saying the advantages and the drawback, and as you can expect, the advantages of one are the drawback of the other. So for the reinterpreted temporal currencies, I explained the main objective is to be able to use it in low current scenario. You also create some new variable that has a physical meaning, the row symmetric and the row asymmetric. And you can also use optimized value to facilitate the studies. But sadly, this optimized value doesn't have a physical meaning. So for example, when you calculate the optimized value, you can end with a W1 vector, which value are 0.1 and minus 0.2 E. So it means you lose the physical meaning. It's complicated to explain which mechanism correspond to these currencies. And after that, when you want to calculate the optimized value, it's way more complicated than the classical temporal occurrences. So for example, for my images, I had to use 41 gigaoctets of RAM compared to 12 for the classical. And it took 25 minutes using 20 processors in parallel compared to only 200 seconds for the classical occurrences. And classical occurrences, as we know, it's easy to understand, it's easy to calculate, but one of the drawbacks is that we can't use it in low occurrences scenario. I'm now going to present you our results. So first I will show the differences between the reinterpreted coherence and the classical one. So for the classical coherence, we can see here on the left a noisy area. So it's fact in a lake. So it's water, so we consider that there was it's supposed to be noise at sea bound. On the right, you can see a field for which there has been a stable plotting for which is around the 25 July, so represented by a red rectangle. You can see that it's roughly the same value of occurrences between 0.2 and 0.4. So it's the first reason that for which we didn't want to use the classical occurrences, because even if on the right we can see a really small peak which could indicate the bluffing, we didn't want to use it because it's as long as it's close to the noise level, we can't really confirm that it's not just a variation. Now if we look at the symmetric part of the reinterpreted occurrences, this time on the right you can see that you have a strong peak for both polarization. So this time it's more easy to prove that there is an eventement. Even more, you have something like a 1 dB differences with the noisy area water. For the noisy area water, this time you have some variation, but to be honest, we didn't spend too much time on it because it's supposed to be on noise area, so we are not definitely not sure that there is any physical interpretation to it. If we look now at the asymmetric part of the coherences, again for the water area, you can see that there is indeed some variation, but we didn't manage to explain them. And for the field, there is two important things to notice. We don't see this time the stable plotting for width, indicated by the red rectangle, but we see a peak indicated by the blue rectangle. So the hypothesis of our agronomist was that it was an early harvesting because in 2022 there was a really huge temperature and therefore fields were harvested a bit earlier than expected. Now I'm going to show you some promising results, therefore using row asymmetric and row symmetric. So one important point is that we managed to characterize multiple events which was the same. So for example, here we are corn flowering, and you can see each time indicated approximately by the red rectangle. When it starts to flower, you can see that we have a huge increase in the row symmetric. Therefore, it means that we should be able to manage to detect this event and date it. You also see that there is a huge drop at the end. Again, the hypothesis of our agronomist was that it was the harvest of the corn because it roughly the date that it should be. Another interesting result is again using the symmetric part of the coherences. You can see that for the width heating represented by the red rectangle, we have a huge increase in the symmetric coherences, and after that, it stays stable. So we know we want to process with more data to see if it keeps staying stable, and if then we can see or not the harvest. So now I'm going to talk about the issue, because as I said, it's our first result, and we encountered a lot of issue. So the first one is that, as I saw you at the beginning, we had a row asymmetric result, which was linked to the harvest of crop, but it wasn't validated by the ground truth. In fact, we don't have any good result validated by the ground truth using the asymmetric part of the coherences. So therefore, we would like to use more data or more ground truth to be able to validate the use of row asymmetric, because it was in fact the part that was interesting us. The second problem is for some fields, we have non-consistent results. So for example, you can see on the bottom left, a result for corn flowering, and this time is a red rectangle. We don't have a huge peak as we had previously. So there is many hypotheses to explain this. One of the easiest will be that we have to check if the field is small, because as I explained, we use a huge window to calculate it. So there is a good chance that there's a lot of noise, in fact, in the pixel describing this field. And the last problem is the use of the optimized value for the row asymmetric on the right, because you can see that we have represented by the red and the purple line. We don't have any good result. For every result, we had something like that. So there is a point we still want to study, so we are already started to talk with Carlos Lopez Martinez, who worked on this project, to see with him if he understands why we have this problem and how we could correct it. So the leftover on perspective. So as explained, there is a lot of research we still want to do. We have all the negative results to try to understand. So the main hypothesis, are the fields too small? Is it linked to the sensor path? Because as we look at a polarimetric currents, the crop orientation, for example, matters too. Or is it linked to another region? For this, we need more ground truth. So the idea would be to use the SYNCO map, because it was a huge project to study the currencies on field. Sadly, I don't know yet if there is a list of the event or not, if it's just the type of crop, so you have to check. After that, like I explained, we have to look at row asymmetric optimized value, because it's supposed to be, in theory, the most interesting result, but we don't have any convex result, so it's a bigger problem for us. After that, I would like to develop a global application. So on the map, you already heard about it. I would like, once we have some confirmed result, to develop an application on it to have an easy use of these currencies, and therefore we need to reduce the processing time. And after that, there is a lot of new cases that we could check, because as soon as you have a low currencies, it could be interesting. So for example, we noted forest in C-band, sand area, and obviously any more ideas that you could have will interest us. To conclude, we think that it's an innovative use case because it will be needed for the new agricultural common policy. So it is important to have this information. Sadly, we still have a lot of research to do because the first result we obtained weren't perfect, as always, so we still have study to do. We think that there is a lot of possible application because as long as you have a low current scenario, depending on the band, it could be C-band, L-band, P-band. In any case, we could use this method to try to detect events. We have the ambition to create an application to share with non-expert users. So therefore, it will allow all experts to process easily their data to check the currencies, or farmers to check the state of the field. And for that, we need to work also on the scalability to be able to have a fast and easy algorithm to process the data. Thank you for your attention. I will gladly answer your question.
Thank you, Nathan. Is there any question in the room? Maybe I can ask the first one. I guess that there are some changes that you can detect in the symmetric part of the coherence, whereas other ones are detected more in the asymmetric part. So do you have an explanation for this point?
Yes, okay. So for example, if I go back to my slide. Okay, here when I presented the advantages of the reinterpreted coherences, you can see here that we have a peak we see using the symmetric coherences, and here we see another one in the asymmetric coherences, and these two peaks doesn't appear in the other coherence. So in fact, the idea is that the symmetric coherences is all the decorrelation which isn't linked to the mechanism, as we saw here in the formula. Here. It is mostly a decorrelation linked to a temporal signal-to-noise ratio, range, or volume, whereas the other decorrences will be more mechanism differences. So for example, in our example, the idea is that when you harvest the wheat, you change your mechanism, because when there is a wheat, you mostly have a volume backscattering, whereas after that, you will mostly have a single bonds mechanism. Whereas when you do the stable pulsing, you don't change the mechanism. You just, it's something we still have to study depending on the event, and that's why we need the more ground truth. Because indeed, we need to understand which event will have an impact or on the asymmetric part or on the symmetric part.
Thank you. There is another question here.
Thank you for the presentation. Just for my curiosity, so for the graph you showed on the right, did you compare that coherent matrix with just the symbol VH intensity? So did you graph the temporal change?
Yeah, we did it. Obviously, it's you also have some variation in the intensity, also depending on the event. Because if you have, for example, an harvesting, you will have a huge differences in intensity. But for something like, for example, for the exactly here the stubble plotting, you don't have an intensity differences. But I think that indeed, in the end, we will need a method we will use at the same time the intensity and the currents.
Thank you.
Armando has a question.
Okay.
Very interesting, really like that. So as you say, at the moment, this it's hard to interpret this projection vector, these omegas that you use. Is there any plan in the future to try to use some transformation which is linear instead than this non-linear, which is the ratio, where then you can keep track? Because it's a linear transformation, then you can still talk about scattering mechanisms. Is there any planning in that direction?
To be honest, no, I didn't think about that, but it's right that if I remember correctly, in the first paper that I cited, they are doing some circular polarization using translation on the scattering vector. So it could be a good idea, in fact, because as our aim is to manage to detect the event, indeed we have to check every polarization to see which polarization characterizes which event. So it's a good idea. Thanks.
I think probably if there is no more question, we can close the session here. Again, thanks to everybody that was here. I really enjoy. Oh, sorry. It's a clap for Nathan. Sorry, Nathan. And so thanks again for staying here. So I would like to remind again everybody to use Padlet for recommendation, or if you have questions that you could not have asked, also for the speaker that was not here, please write down in Padlet. We will use it also to create the recommendation for last day, or we can come and pick your brain during the coffee break. Yes. I think Francesco has an announcement.
I don't want to be boring because I'm always telling the same thing. But for this Padlet, we decided that we will keep it open. We can keep it open after the conference, maybe even until the next PolInSAR for 2 years, because it could be a continuous basis for exchange of ideas, recommendations, proposals related to polarimetry. So, for example, for the recommendations which correspond to actions that we would like to accomplish and to proceed from one PolInSAR to the other, it's I think it's a perfect place to show what we are doing and also to get your continuous feedback. So don't use it only during this week, but have a look at it also later on.
So I guess we reconvene at 2:10. 2:10. So in yeah, about 2 hours, right? No, 1 hour. 1 hour, 10 minutes. See you later. Thank you.
già due persone dietro di te.
So, who will be the first?
E Sabrina, aspetta.
Vado a prendere le presentazioni della seconda sessione,
Sì. Allora, te
Land application, I guess.
yes. Sabrina is coming. 1 minute is coming.
It's coming there?
No, yeah. Because doing the computer che yeah. No. Sabrina lock, control, everything, e poi Sabrina is keeping for me. You can wait 1 second. It's coming. Thank you.
You're welcome. Next.
Biomass. Yes, biomass. Yes, of course.
Just say so.
We know. Okay. It's the instruction. Normally we ask for
Do you want to go?
the PowerPoint.
Oh, okay.
Then the
check on the
let's say the final version will be PDF.
You're welcome.
Okay, it's
Staccare da te.
Hi, I'm the number 2.
Oh, okay.
We'll open it.
Okay.
I know. We already tested it. Okay. It's okay.
So this is the screen I will see from there? No, you will
The
see
PC is not connected with the Wi-Fi, so it's redline, so don't worry.
I can't
So I tried it.
No, I can't.
But the
Maybe
PC
it was when the
No, Jacopo
You will
told
see
me
the slides
that
on
the
the pool
PC
on the
are in
laptop.
the Wi-Fi for the presentation. Yes, go ahead. The PC for the presentation is in the LAN, not in the
Wi-Fi.
So the problem is I have to test mine because I will be with the Wi-Fi for WebEx. So I will test it after.
I don't know. Maybe it was because there were too many people in the room, and then it starts to.
No, but if it is like this, I ask for a LAN cable as well. We have, so they offered us. For me, it's better to have the LAN cable since I am the host.
Exactly.
No, I don't want to be. By the way, we have backup in ISA, so I have my colleagues Will Irene who are the.
Exactly. Okay.
Yeah. No. So,
How many people do we have online now?
I'll tell you. I mean, it's really Fabrizio from Esri say we didn't have so much people online. No, it's not true, eh? And I told him
Me la sto volando, vedo che sei tutta
No.
I mean, on the last day we put on the website.
Apart from no. But I told Doris to spread the word around the divisions.
A parte che
I told Doris.
quando te ne accorgi è troppo tardi, però.
No, I didn't tweet because I would like to make a wrap-up tweet, otherwise it would be, let's say, many tweets during the days that it will be one tweet plus one newsletter in LinkedIn, and then collecting all the pictures.
C'ho troppa ansia su sta cosa.
Yes, thank you. So it's perfect for me. Okay. Thank you so much. Welcome. Thank you.
Comunque 45 euro lo schermo. Okay.
The views on who? Yeah. The Padlet. The
I will never learn it. I'm too stupid.
No. So,
say the most important. Today is the most important in the future. Most important person in the biomass.
yesterday we had 272 people viewing the live streaming, but we didn't have the proof.
In the closing, you will make kind of slide. It would be good to have
Send the Klaus the statistics.
we can make it together if you have time for.
I have to give me the time to make some statistics.
No, you have time.
No.
Day before, the last day.
Yeah. Okay.
Just put some print screen of statistics. We put them together. I think doing that. I think it's nice.
This is the most familiar.
In the presentation, so years later you'll find it.
No. This is one of my in my pipeline. I will do.
Can I ask you something?
Yes.
The presentations here.
Which one? The biomass?
The
Yes.
one that played this morning. To copy them. And if there is you can modify them. This one is in the second folder.
Aspetta, Clement. Dammi questo.
Io ho finito tutto.
Mettilo
I
qua.
think there was a mistake in the second folder.
Vai, mettili sicuro.
Dipende quello. Cioè, tutte e due.
The first one is not there.
Sì, sono un po' più alti. Sì, la mia guarda è meglio. Sì, secondo me è un po' più alto.
Ah, because Jacopo, the first one, la prima di quella sala, dove sta?
No, ti ho già inserito sulle cartelle mie.
Ah, ok,
Dove
ce l'ha
te lo do?
Jacopo.
Ce l'ho io la prima,
Così
manca proprio la
devi
prima.
diretti tu, Jacopo.
Che è una PDF.
We have to make the photo, huh?
Klaus.
We have to make the photo, huh?
Klaus.
You said we should make a photo, huh?
Even all together?
Yes.
So we can do this by using
That's
both
well,
polarimetric and interferometric information.
No, but you meant.
Oh, you meant
At Elva,
I was mentioning the.
we have very high
You mean the group?
Yeah.
No, I thought you was No, okay, we don't want that.
Can I close this?
baseline with the residual baseline correlation that
Okay, so.
larger than the
Le registrazioni sono così, guarda.
So what we can do is we can go to larger baseline.
Cioè tu, così non ce l'hai anche solo presentazione.
And here we have a baseline of 20 meters, and then we can bring back
This is registration è solo presentazione con l'audio, uno o l'altro, tutte e due. C'è la possibilità di tutte e due.
What
do you like, the one with the people talking or the one on the
Tutte e due. I give you yeah.
part of the forest
Yeah.
Ce l'ha Jacopo.
Uno, sì, ce l'ho già, te lo subito, te la prendo.
No, bene.
Te la prendo subito.
Quale chiavetta mi posso
Piace più quella della camera. Con la faccia. Però non prima tutti e due. Ah, vogliamo trasferirli già?
Io e il mio comincio a fare.
Perché ci vuole, Allora, lo devi aprire, la cartella, te la
Allora,
prende la 1.
Sì, la prima della presentazione.
La prima
Me la devi portare pure a me,
Did you need it? Yeah, for first time? Yeah, I think it's okay.
Yes.
Après sa présentation, et il a dit qu'il est sur son truc, mais il va lui dire
Ok.
si c'est mieux que
D'accord.
je te demande.
Quand tu préfères. Moi, pour la session, cet après-midi, je m'occupe de la session des biomass. S'il doit faire un upload, tu demandes, il y a un technicien.
Non, il n'upload pas. Non,
Ok.
sa présentation le premier jour.
Ah, les premiers jours, ok.
Oui. On a
Ok.
le droit de les prendre.
Si tu veux, je te les...
Oui.
Ok,
Oui.
ok.
Donc, tu regardes si...
Non, faisons une chose à la fois, comme ça.
Aïe, comme ça.
Alors,
tu mets le mien. Je vois plus moi.
voilà.
Alors là, attends, tu tapes la date. Attends. Ça, c'est
Attends, je dois faire comme ça. Title, view.
Non, the time, c'est enregistré. The last one, maybe. C'est ça. C'est pas le temps.
Allora, te voglio aprire una cartella, facciamo cartella mia e cartella tua. La pennetta e il numero qui. Facciamo questa qua.
Tutto su una chiavetta mi sa che c'entra,
Come no?
Non voglio essere pessimista, però
Sì,
io ho almeno 10 giga giù.
64.
Aspetta, no, c'ho forse 7 giga. Vabbè, sì.
Facciamo, che schifo? Nuova cartella, una te e una io. La cartella.
Metti streaming 2 e
Alla streaming,
live.
come si scrive streaming?
Streaming.
Con camera. E poi invece la tua è la.
Metti slide.
Ok. S.
Slide.
Donc,
Più audio.
Is this one? Et c'est celle-là?
ouais, c'est là. C'est là. On peut faire rapidement comme ça.
Si.
È una cosa del...
On a le temps.
Il programma è.
No, salva prima con invio.
Voilà.
Senti.
Ça c'est bon. Et maintenant,
Tegna diretta,
Michael,
la blocco,
je
revia il
te
computer.
copie
Da
ici
stamattina
la...
sta problemi. Revia proprio. Ma sono spenti quei microfoni? No, è un po' quel microfono. No, non è. È acceso. Ma tanto chiudiamo questo qua. Fabrizio dovrebbe rivedermi,
Vediamo un attimo.
Ok, adesso prima era caduta la linea, ma va bene. chiamata soltanto per chiederti se la fattura mi è arrivata. Provo a contattare la tua cooperativa, ma mi sembra proprio impossibile contattarli. Gli fai la gentilezza e mi devono modificare la fattura che mi hanno mandato, perché non capisco perché mi hanno mandato quella data 13 di maggio, che io in teoria il 13 maggio non ho proprio lavorato. Visto una cosa fiscale, mi serve le date giuste. Gentilmente se mi modificano la data e anche se mi puoi dire per capire il prezzario della cifra totale che mi è arrivato in fattura, per capire soltanto, solo per sapere, basta, sulle divisioni sui giorni. Grazie mille Alessandro. E Alessandro, senza che ci devi detto, perché mi hai 18 tanto mi serve soltanto che senti la tua cooperativa di farti fare la fattura, perché quella che mi hanno mandato è sbagliata. Hanno scritto il 13 di maggio che io il 13 di giugno. No, no, prego, prego. No, grazie mille. Ciao Fabrizio, scusa che ti disturbo. Potresti vedere un attimino la diretta come la vedi? Perché ho dovuto riavviare il computer che si è un po' impallato. Grazie. Così te la pago subito, sì sì, per 2 mesi te la pago. Devi farlo partire. Controlla il video perché veramente non so più. Poi controlla la USB per la controllo io. Cioè, se io chiudo questo computer non si deve. Questo lo lascio il microfono aperto.
Someone wanted a microphone?
No, because we hear something coming inside our software.
Okay, I think we can start.
It's nobody to kick my. There's no Magda on the other side to say no.
Good afternoon, everybody. Welcome to the session on land applications of polarimetry, polarimetric interferometry for land. We have 5 presentations, and in fact, I have a pleasure to introduce the first speaker, and I already told the speaker that I'm very happy that I can introduce her, because since my first PolInSAR, I remember Elisa working for urban applications, and there were many other researchers that were also trying to do similar works, but she survived. And we have one presentation today about PolInSAR for urban areas. So welcome, Elise Collin.
Thank you. Thank you very much. So I'm Elise Collin. Good afternoon. I'm sorry the lunch was very short. I'm very pleased to be here to present my last study on the benefit of polarimetry, especially for urban areas. And I call this PolInSAR. It's just a suggestion of Professor Eric Potier. So here is the first image that I propose to highlight the benefit of polarimetric information, because this colored image has been made by using only polarimetric parameters that are span invariants. That means there is no intensity information in this image, so you can see the information purely added by the polarimetry information. It has been computed over time series of Terrassa X images over Toulouse, here in France. So first, why I consider that time series are a chance now, especially for high-resolution images, because in polarimetry, you know that there are 2 kinds of parameters. We could say first-order parameters corresponding to intensity, for example, in the lexicographic basis or poly basis. And we have also second-order parameters. That means as soon as we have to compute the cross product or the intensity power of different polarimetric channels, such as a correlation coefficient between 2 polarimetric channels, or such as the coherence polarimetric the coherency polarimetric matrix. And when you want to estimate these second-order parameters, you need to have several samples to estimate the coefficients. And so traditionally, it's made by using a simple boxcar filtering. That means by using different pixels in the neighborhood of the pixel under consideration to be able to estimate this parameter. And what we propose here is just to benefit from the time series information to estimate these parameters by using all intensities or all polarimetric amplitudes according to time for a given pixel. So first, I will try to see how we can highlight deterministic targets with such approaches. By deterministic target, I mean a target that will transform the polarimetric state of the emitted wave into another polarimetric state, but still deterministic. And on the contrary, by non-deterministic target, I mean something that will transform the emitted polarization state into something that will be random according to time or partially random, changes over time. And so I will mainly consider here dual polarimetric time series, because we have most often dual polarimetric cases, especially with Sentinel-1 time series. I mean either HNV or VH-VV. So in this case, you can consider that each acquisition that you have in one pixel can be considered as a Jones vector. That means that the emission polarization state is fixed, either H or V, and you record the signals for both polarimetric channels, H and V. And each of these polarimetric states can be described by an ellipse, which can move according to the time. And for each polarimetric state, you are also able to estimate the orientation and the ellipticity of this ellipse. So if you want to study the variations of all these polarimetric states, there are at least two mathematical tools that are strictly equivalent. The first one is the coherence covariance matrix that is just computed by using the cross correlations between the two components of the Jones vector. Or you can also consider the equivalent Stokes vector, which is a real 4-component vector. Both are strictly equivalent. In the first case, you can consider that the coefficient of the coherence matrix can describe the eigen polarimetric state of your time series. Whereas in the second case on the right, you can see that you can represent your Stokes vector in the reference space of the Poincaré sphere. And you retrieve the same red point here corresponding to the main eigenstate of this time series. From these two formalisms, we are able to compute the degree of polarization, either from the Stokes vector or the coherence matrix. And you are also able to describe the main eigenvector, so the main state polarimetric state, by the orientation and the ellipticity. And from these three parameters, I proposed here to make a false colored representation by using the hue saturation value colored space. For the value, I use as brightness the coefficient, the degree of polarization. For the hue, the color of this representation, I use the main orientation axis of the eigenvector. And for the saturation value, that means how bright the color is, I use the ellipticity of the main polarization state. And so it's like, it's with this method that I can obtain the following colored representation. We can also propose another polarimetric representation of these parameters by using, once again, for the intensity value, the total span, average span of the time series. And you can see that it's able to enhance very well all deterministic targets in the area here. If I got here a zoom on the wall footprints, you can see all the buildings that appear in bright colors, on the contrary to trees that are more in gray levels. And we have a nice building case here, which is a nice example of what we call a tripod. That means three parts of the buildings with different orientations around the wall possible orientation in azimuth. So in the second part, I want to just to suggest how to use polarimetry to improve our capacity of change detection. And I will come back to next previous presentation about the reactive algorithm. I don't know if you know it already, but it's an algorithm that allows to enhance the changes, all changes occurring during a given period of time between two dates by using the whole time series between these two dates. Here is an example of what you can obtain with this kind of representation on the port of Singapore. And the K parameter in this algorithm is the coefficient of variation. It's simply defined as the ratio between the standard deviation and the mean of the amplitude or intensity contained in the whole time series. So if this coefficient
correspond to typical speckle, which is stable, uncorrelated, but stable in time. You have typical value that you can predict theoretically. Whereas if this coefficient is very low, you have a permanent scatterer, and when this coefficient is typically higher, you have a change. So the idea is now how to benefit from polarimetry to extend to the polarimetric case this kind of coefficient of variations. So now there exists 4 different possibilities to extend to the multimodal case this definition of coefficient of variation. The first one was proposed in the 60s. It has some drawbacks because, for example, if one polarimetric channel is very stable, so if one eigenvalue is close to 0, the whole multimodal coefficient is close to 0. The second one involves the trace, so it's better concerning the first points, but it doesn't it doesn't it doesn't take into account the cross products between the different polarimetric channels. The third one takes into account these cross products, but it's very sensitive to noise because it implies also the inversion of the coherence matrix. And the fourth one, the last one, is proposed more recently to avoid the previous drawbacks. But not that you have to apply this multivariate definition to a vector with real components. So if I want to apply this to my time series with HV and VH, we have at least 2 possibilities. The first one is to apply it only on the modulus of each component of the vector, but you are still not able to take into account the cross correlations or the information contained in the phase between the two channels. Another solution that I propose is to use the Stokes vector again, which transforms the previous one in a 4-component real vector. And so you can use it directly to compute the multivariate coefficients of variations. So just some preliminary results considering the first approach. Here on a small extract of the whole footprints over Toulouse. On the left, you have the result of the reactive algorithm, highlighting in colors the different changes. So you can see that there are some buildings under constructions, for example. In B, in the second column, you have a superposition between the Bose intensity relative to each polarimetric channels. It is just to see how different are the information in intensity contained in the Bose polarimetric channels. In C, you have the classical coefficient of variation obtained in VH. And in the last column, you have the multivariate coefficient proposed in the last version. And you can see highlighted in the yellow color that it allows to highlight changes that weren't visible with the classical approach in one polarimetric channel. Other results here, when you apply these methods also with the Stokes vector on the second line of the results. On the first column, it was the first proposition of multimodal coefficient of variation. So once again, you can see that there is this problem, or this effect linked to low values for permanent scatterers, because as soon as one polarimetric channel is very stable, the coefficient will highlight the whole polarimetric information as stable, which is not necessarily what we want to obtain. The other versions are quite similar. We need some more time to see exactly what are the differences. And finally, to conclude, I would like to emphasize the link that can exist between this kind of multimodal coefficient of variation and the degree of polarization or the depolarization effect, of course. Here is an image of the degree of polarization computed for the whole image over Toulouse. And here, by comparison, here is just the inverse of the coefficient of variation. That means that for high values, you should have permanent scatterers too, a little bit as it is the case with the degree of polarizations. But most differences appear only on areas containing changes, because in this case, it's very difficult to interpret what is the degree of polarization of one target, which will vary, we will change according to the time. So as a conclusion, from a dual polarimetric time series, HHV or VHVV, we have seen that we are able to compute a degree of polarization or depolarization without loss of resolution. We are able also to define the mean orientation angle or ellipticity still without loss of resolution. We can also extend the notion of change detection to the whole polarimetric case with different alternatives. And we can consider the link between the polarimetric depolarization effect and the temporal decorrelation effect also. I would like just to say that for all these cases, you really need to have available the information of phase between the different polarimetric channels. That is something which is only available in the SLC data, of course, and my feeling is that we still need to have some platforms to be able to process this kind of time series for SLC information. At least without necessarily to download or to process the whole footprint of the image. That can be very huge in Sentinel-1 cases, but it would be very great to be able to do this task only on a small footprint of the whole footprint of the image. I have put on our archive some papers in open source that you can discuss with me. Of course, I would be very pleased. The first one on the benefit of polarimetry to be sure to detect all changes occurring during a time period. The second one on the way of compute, degree of polarization and orientation ellipticity. And the last one on the coefficient of variation extended to the polarimetric multimodal case. I thank you for your attention. I would be pleased to answer your question. Thank you.
Thank you. I see that there are questions.
Thank you for your presentation. When you measure the coefficient of variation, you mentioned that if it is low, it is permanent scatters. I see that your point has been on urban areas, but if you look into forest, so it doesn't mean that necessarily that is a high coefficient of variation is changed. It could be because for distributed scatters, the values of coefficient is also high.
Yeah, but traditionally, if you consider a homogeneous distribution of speckle over natural areas, you will see that you have a given distribution. Which will follow also a Rayleigh distribution if you compute it on an amplitude, for example. So you know that it has to follow this distribution if there is no deterministic part in the signal or if there is no changes. So if you can put a threshold and deciding if this behavior is outside the classical statistical behavior. Even on natural areas. Yeah.
Okay, thank you.
Is there another question? I also have one.
Yeah, probably I'm the wrong person to ask this, but my question is, what would you do if you would have a much higher spatial resolution image? Would you compromise polarimetry in this case, and you would get also the features? Or is it still that you get the features even with high resolution images?
So for lower resolution, such as Sentinel-1, for example, if you compute the degree of polarization, I guess I have another slide, but I don't know if the just after this one, I don't know if it's possible to to show it. So the degree of polarization is still very interesting on Sentinel-1 images, and there is a little bit more contrast, I would say, because I guess that you can see different effects between different degree of polarization or depolarization between surface scattering or volumic scattering. So I would like to see further if you can see different behaviors such that. Concerning the orientation here, as you can see, the color is main concentrated around the azimuthal main alignment between the trajectory and the object. I think it's because there are less deterministic targets at these scales with a strong deterministic, strong enough to be deterministic enough, I would say. I'm not sure to understand exactly what is going on, but we have to look further, yeah.
Yeah, thanks.
Cool. Very quick question from my side. It's very interesting to see what you're showing. I think you're poking on an assumption that we do, which is ergodicity. And
yeah.
So it's very cool to see that you're just working in that direction. Have you tried to see the degree of polarization in time and see how you compare to the degree of polarization in space?
Yeah, classically, at the beginning, we did a degree of polarization in a spatial way, classically, and it gives very poor results, especially at high resolution, and in urban environments, because when you compare one pixel containing perhaps one deterministic target or some details of the walls of the building with a next close pixel, they do not contain at all the same information. I mean, it's very different between the small scatterers that will create the signal. And so you create a false depolarization, I would say, more linked to the spatial heterogeneity of the pixels that you consider.
Sounds very good. When you apply on some fully developed speckle, do they look the same, spatial and temporal, like for forests?
Yeah. On natural targets, it's okay. It's really a problem when you consider deterministic or details or things like you can see in urban. Yeah. Thank you.
Thanks, Elise. We can move to next paper for today from Saporta Paloma from DLR and ETH, assessing polarimetric SAR interferometric coherence region parameters over a permafrost landscape. The floor is yours.
Thank you. Right, it's nice to see so many people interested in permafrost. So, hi everyone. Today I will present our first analysis regarding PolInSAR coherence region parameters over our permafrost landscape. I'm working together with Alberto and Irena at DLR and UPC, respectively, or the other way around, rather. Up. So first of all, what is permafrost at all? Probably most of you know, but permafrost is defined as soil that remains below 0 degree for more than 2 consecutive years, meaning it's not ice, it's soil that is frozen. Now I think it's quite clear. Turns out permafrost covers about 1/4 of the northern hemisphere land, and because the temperatures there are changing much faster than in the rest of the world, it's undergoing quite rapid change. This degradation translates, for instance, into, so the degradation of this active layer we'll be talking about right now, and this has implications at the local scale, triggering landslides, mass wasting, changes in the local hydrology, but also damages to settlements and infrastructures. But it also has impacts at the global scale. And why is that? Because there is actually quite some amount of organic material that is stored in perennially frozen grounds. And so you imagine that when this frozen ground starts thawing, then this leads to the mobilization and decomposition of this organic matter and potentially to release of greenhouse gases in the atmosphere. And this could possibly change the permafrost from a greenhouse gas sink to a source. So not great. Oh, yeah. Right. So actually, see, if you check out this map that shows the location of permafrost, you understand that permafrost monitoring benefits greatly from remote sensing, because those areas here are precisely the areas where there's not so much population and less infrastructure, meaning that doing ground measurements is costly and also difficult. Therefore, the interest of remote sensing. And for now, radar remote sensing, at least INSAR, mostly is focused on differential star interferometry to measure the subsidence of the ground, either within a season, a thawing season, or between the years to measure the subsidence and degradation of the ground. And here today, we propose a bit of a different approach, which is our first, but also, to my knowledge, the first, I don't know, PolInSAR analysis over a continuous permafrost region, or at least a zone, in the Canadian Arctic. Right, we want to examine the influence of the land cover types, the vegetation, and the season on the PolInSAR coherence regions. So this is what we're going to see now. But first, let me show you a tiny bit what's so specific actually about permafrost, and let's see a bit what the seasonal dynamics are. So in the winter, what happens is the ground is entirely frozen. So this is the ground, right? Mind the colors. The colors don't correspond to soil type, but to soil thermal state, frozen and frozen. So the ground is completely frozen, it's permafrost, right? And it's frozen from on a depth of about tens of meters to hundreds of meters. And we have some vegetation that's covered by snow. And the reason here is actually temperature, I forgot to mention, but reach up to minus 40 degrees, so everything's frozen. We also have the presence of ice, either in the form of ice wedges, this kind of trenches you see here, or also sometimes types of lenses. And now, when the temperatures start to get higher, then you see what happens is that the snow melts, right? And then this upper layer of the permafrost that was frozen in the winter starts to thaw. This is normal, happens every year. And this happens until it reaches a certain maximum, the maximum thaw. This part here on top, we call the active layer. It's a very important parameter for permafrost scientists. And then when the temperatures start to decrease again, then we recycle back. Right. Up. So, in order to investigate the interaction between permafrost soils and radar signal, the DLR conducted an airborne campaign, the Permafrost Airborne SAR experiment campaign, in actually many sites in Canada, but today we focus on one, which is this site here in the northwest Canada, on the Arctic coast, and it's a tundra area. Just some details. So there were 2 successive missions within the campaign. So the first one in the summer, 2018, and the second one in the winter. You see now, you understand there was those differences in the state of the soil itself. And the radar was operated at several bands, fully polarimetric, and actually the performance of several baselines is what makes this data set quite unique. Not quite unique, just unique, actually. Yeah, this is the area we focus on. This is the SAR footprint on this area. So you see by the coast. Actually, this is a lake. This is not exactly the coast. And the reason, one of the reasons why they chose this area is that it's a quite well-monitored area. This means also for us that we have partnerships, and in particular, we have access to a certain amount of ground truth data, or at least, ground truth data. For instance, the land cover, the precise digital terrain model, among others. And let's take a look a tiny bit at what vegetation we have there. So you see we have isolated trees. We have tall shrub, 1.80 meters, this range of magnitude. We have riparian shrubs that are shrubs that grow along the streams. And then we have other types of shrubs, smaller vegetation, and even smaller vegetation. This is what we expect. And those maps are provided by the Alfred Wegener Institute. Yeah. So our workflow is the following. So we compute, so in the PolInSAR space, we compute this optimized phases, and from this maximum phase extent, we derive maximum height extent, because we know this is related to the vertical reflectivity function. And we, from the phase, max extent in phase, we transfer to max extent in height, and then we compare, we use our ground truth data, or ground truth ground truth data to compare. So for the next, I'm pretty sure everyone knows this, but really briefly, so we start from the scattering matrices, build the scattering vectors, we build the different coherency matrices, and then finally we do this polar decomposition of this P matrix, and we end with the eigenvalue decomposition of this U unitary matrix, and by analyzing the eigenvectors and taking the maximum phase extent of the eigenvectors. So this is how we get our phase extent. Now, let us see what the results are. So what do we have? On top, we have this delta height from the delta phase that I was just talking about. Below, we have the reference vegetation height, and on the right, we have the scatter plots ordered by land cover types. And here, I don't know if you see, but so we start lichen moss, dry hummock, tussock, dwarf shrub, single shrub, riparian shrub trees, meaning by increasing vegetation height. So they're ordered here. And the first thing we see is that this relative change is conserved. So this is actually quite good news. And another thing we see is that, I pointed out, even though this is not our main topic, but still, because it's there, the tree heights are underestimated, but this is not, anyway, we did not really expect to retrieve tree height, do we? Because anyway, we're not sure that we reach the ground, and that there's not a bit of penetration at the top. I forgot to mention, we have here 100-meter baseline, and we are looking at L-band. Yeah, and then we come to the smaller vegetation types, so the 4-5 here, yeah, absolutely 5. And it seems here we have this kind of height of 25 centimeter when our reference data is much lower. And here we have two possible explanations. So the first one is that this vegetation height is derived from airball laser scanning, a full waveform LiDAR. And it can be that if the vegetation is a bit dense, it misses the points on the ground and therefore underestimates its vegetation height. So this is one possibility. The other possibility is that here this height or phase is related more to noise. I will talk about it a tiny bit later. Up. And now this is the result in the winter case. Remember when the ground is frozen. So what we see is that first, those tree heights, they decrease. Well, maybe it's not the first thing we see, but I pointed out. And this we explain by the fact that when in the winter with the very low temperatures, the trees are mostly, not completely, mostly frozen, and therefore they become transparent for the radar. What we also see is that those smaller vegetation types, you see they've been shifted up, right? They were 25 centimeter approx, and now they are around 50. So there's a kind of increase. So the way we interpret it is that we suppose that there can be some volume decoration to do penetration into the frozen ground, and this would explain this increase of phase extent and therefore height extent. Right. Actually, we conducted some error estimation to kind of go in the same direction, because we take the center of the coherence region, and from this coherence norm, we can compute the error associated, not the error, but the variance, and therefore standard deviation associated to the phase, and transform this into height, right? And we see that actually, indeed, we have higher standard deviation in the winter case, and we interpret it the same way as an effect of the volume decorrelation because of penetration in the ground in the winter. Let us take a peek at a smaller area, so a little zoom. So this is area that's close to some research station. What do we have here? We have a lake, we have some tree patches, we have a certain creek here, and otherwise mostly small vegetation and some shrubs. And this is the optical imagery. Yeah. So this is the results at L-band in the summer. Actually, what we can do is just compute some kind of max filtering to emphasize a bit the features, because otherwise we don't really see much. So now so it's the exact same, but just filtered a bit to emphasize the features. And if I now add the winter L-band, but also C-band, we see the different things, right? Let's focus on L-band. What we have is that we have features that appear that were not there before, those features here, for instance. What we also have is that overall, it seems there's some kind of increase. I mean, we talked already actually before, didn't we? At the C-band, it's quite different. first thing we see is that both are not so different from each other, and we don't have this kind of increase. What we also see is that there are kind of features that disappear from the summer to the winter. Those plots, those patches here, and here, here. Not this one, this one. Anyway, we don't find them again in the winter case. And this we interpret as, turns out those areas are areas with dwarf shrubs, and the way we can interpret it is that they freeze, or mostly freeze in the summer, becoming transparent, and therefore they're not reflected here anymore. Right. Actually, let us look at some scatter plots actually this helps us to confirm those observations we have from before. So from the summer to the winter in L band, we have ordered again in the same way. We have this overall increase that we've seen, and in the C band, we spot actually that indeed we have no change or decrease for just one type of vegetation, which is the dwarf shrub. What we also see is that if we take now summer versus winter, that in the summer, we have quite a clear discrimination with the land cover type, or the vegetation type. And this is not the case anymore in the winter. Yeah, so this kind of suggests that the signal that we see is related more to other factors than the vegetation itself. Yeah, so I don't see time really, but anyway. Sorry? Perfect. Well, this is the last slide. So to conclude, what did we do? We made this first PolInSAR analysis over permafrost area, so at L and C band. The main outcome that we have is that in the summer we can discriminate as we somehow expect, I suppose, the PolInSAR coherence region extent by land cover type. However, in the winter, when we have frozen vegetation and frozen ground, meaning lower dielectric constant and supposedly higher penetration, we have an increase in this delta height at L band and little to no change between summer and winter at C band. Our next steps, or what we further want to do next, is to build an EM model to relate those observations to some other, the parameters of snow penetration and vegetation transparency. With this, I thank you for your attention, and if you have questions, please go ahead.
Thank you. Very interesting to see this work on permafrost. Is there any question from the audience?
I just wanted to ask, what was the spatial resolution of your data?
Yeah, so we perform multi-looking and also some other type of filtering. So in all the products I've shown, it's 5 by 5 meter. Yeah.
So I may have a question for me. From the plots, maybe by eye, that are not very good, but it looked to me that C band has deeper penetration than L band.
Yeah, but so the thing is that at C band, we would probably interpret this height not really as a penetration depth or even it's not clear if we can interpret it as an extent really because of the polarimetry polarization at different heights, or simply because of the larger decorrelation. Okay. Yeah.
So it goes closer to the center, and so they spread.
Somehow, yeah.
Yeah.
So there's still ambiguity.
No,
yeah.
It's okay. Yeah. Another question: is the plan then to use these things into a model so that then you can convert these appearance differences into actually height of the permafrost? So are you building a model for interpreting these results?
Yeah, so height of permafrost, I don't think so, because anyway, the permafrost is much deeper. We don't expect to reach the bottom of the permafrost, which is thousands of meters. Now, if we can convert it to, so the interest for us is the soil parameters. So in the end, what we're interested in is the penetration within the ground. So yeah, but then I lost the track of your question.
I think so. So you're building a model out of this.
Oh, right? Yeah, right.
Yeah, that was the question.
Sorry.
Are there any other questions? Thank you again for your presentation. Yep.
Thank you. The next presenter is Georgina Page, who will present a work about monitoring peatland water depth, water table depth using polarimetric SAR.
Hello, I'm Georgina Page, and I'm a PhD student at the University of Stirling, and this is my presenting on monitoring peatland water table depth using L-band polarimetric SAR. I'd like to acknowledge the lead author in this paper was Benjamin Serrat, and the other authors are Christian Silva-Perez, Peter Hunter, Jens Subke, and Armando Marino. So the main aim of our research was to look at the extent at which machine learning approaches can be used to measure and predict the water table depth using polarimetric SAR. So first, a bit of background about what peatlands are. So peatlands are a type of wetland, and they're really important ecosystems covering about 3% of the land. They're really important because they have a very large store of carbon. About a third of all soil carbon is found within peatlands. This carbon is stored in the form of peat, which is a type of soil that has 30% or more dead organic material in it. And the peat is formed from peat-forming vegetation, such as sphagnum moss. This moss thrives in waterlogged conditions, which is why it grows in peatlands, and the reason the carbon is stored is because this waterlogged condition, the high water level beneath the surface, prevents vegetation from decomposing using aerobic decomposition, and therefore can only decompose using anaerobic decomposition. This is a much slower rate and is the reason why the carbon can be stored in this way. So the issue is that a lot of peatlands have been degraded, so they have been partly destroyed, the land has been drained to be able to build on, or the land, the peat has been dug up and used for burning to use for fuel. So when the peatlands are degraded, the water level beneath the surface drops, and the vegetation and the peat can decompose much faster, releasing a lot of greenhouse gases and carbon emissions into the atmosphere. So the degraded peatlands are responsible for about 4% of all anthropogenic carbon emissions, so it's a contributor to global warming. So therefore, it's important to help restore these areas, and this can be done by raising the water level, by putting in dams or filling in the gullies that have been dug out. So this can be important to monitor in short and long timescales, and the key way of doing this is to measure the water table depth to check that it is at a better level than previous. So this can be done in person, but it's very time-consuming, and hence remote sensing is used. So some research previously has used optical and C-band SAR imagery to predict the water table depth, and so far it's got an R-squared value of 0.41. This therefore led to our hypothesis that by using L-band quad-polarized SAR would improve the accuracy of these measurements. L-band because of a greater ground penetration, and fully polarimetric nature would give more information about the subsurface details. So onto our study area, we looked at Flanders moss, which is a peatland, a raised bog in Stirlingshire in the middle of Scotland. The reason for choosing this site is because there are numerous water table loggers at this location. Nature Scott has 34 loggers here. So we were able to get data here for ground measurements to be able to compare to the satellite data. We looked at using ALOS2 data, and we looked between 2016 and 2017 to be able to identify dates that there were overpasses of the satellite and there were measurements taken on the ground. And we were able to get 93 data points at this location. So here is a few SAR images showing the Flanders moss over the 3 particular dates that we looked at. So this was 7th of March 2016, the 12th of April 2017, and the 29th of May 2017. So onto our processing, we wanted to identify, look at multiple different variables to see what contribution would have on the results. So to do this, we processed satellite data numerous times. We did 4 different speckle filters, so Boxcar, Refined Lie, Improved Lie Sigma, and IDAN. We did 4 different speckle filter sizes, and we did 6 different polarimetric decompositions. So HA alpha quadpole, Huygen, Pauli, Tuzi, Van Zyl, and the Yamaguchi. So from them, we had 32 different parameters that we calculated. So we looked at processing for each different possible combination of these, and that gave us 512 observable data points to look at. Following on from this, we added a weighing coefficient. So we looked at the pixels that were between up to 50 meters away from the waterlogger, and we averaged them. But each of the pixels had a weighing coefficient so that the pixels closer to the waterlogger will have a more significant impact on the results than the ones further away. This weighing coefficient had a decreasing exponential component, as seen on the graph, and we tried it with 9 different weighing coefficients, so from 0.001 to 0.5. We did this with each different possible combination, as mentioned as before, so 512 times 9, and we got 4,608 data points. So rather than just looking at the absolute water table depth, so the actual distance beneath the surface of the water level, we wanted to look at the standardized water table depth as well. So we found the mean value for each location and took this away from the absolute value and divided by the standard deviation. The aim for this is to therefore not just look at any temporal changes, but by finding the averages and the standardized value, we could eliminate some of the spatial variation that was having an effect on the radar signal. So this is likely to be a surface roughness or vegetation that was impacting some of the results. So the next part of our method was we had over 4,000 data points, and we wanted to narrow it down. So we compared them to the water table depth and found which ones was most correlated to the water table. And this, we chose which one was most correlated to water table for each different polarimetric decomposition parameter. So this left us with 31 observables to work with. We then processed the data through 2 different machine learning approaches, so random forest and relaxed lasso, and used the models to predict the absolute water table depth and the standardized water table depth. We also validated it using 2 different methods. So there was leave one out cross-validation. So this was separating the data points into 78 fields, and then a section of that was left for validation at the end. There was also the leave location out cross-validation. So instead of just leaving odd data points out, this was leaving out an entire waterlogger section. So therefore, when it came to predicting this area, there was no information in the test set of data, so therefore it was predicting a new area. So onto the first part of our results is looking at the box plots showing the water table depth over our time frame. So the top graph shows the water table depth changes from March 2016 to May 2017, and it shows that the water table depth did decrease in this period. The bottom graph shows the standardized water table depth, and it's more obvious that the water table has decreased in this graph. By May 2017, all the points had a lower than average value, indicating that it was a much drier period at this time. So onto our results that show the model results. So this shows all the combinations showing the absolute water table depth. So we have the random forest versions and the relaxed lasso. The top 2 graphs indicate the leave location out cross-validation, and the bottom 2 show the leave one out cross-validation. So none of these results gave us a significant result that we were hoping for, but what was obvious is that the leave one out cross-validation did give a slightly better result, but this was then validated with data that had a bit of knowledge in the test set of data. Also, the random forest method had a slightly better version over the relaxed lasso. So from these, what we got was R squared of a 0.2 as the best, but still not significant results. So therefore, we looked at the standardized water table depth. And so this graph shows the relaxed lasso approach using the leave location out cross-validation. And this did give an improvement of 0.38 for the R squared value. So this is more significant. As seen on the graph, in the lower left corner, the yellow points indicate the May 2017 results, showing a more different variation between the dates that by this day there was a lower water table depth compared to the other dates. The next improvement was therefore using the random forest approach. So this graph shows the standardized water table depth, using random forest and using the leave one out cross-validation approach. And this gave us a better value of R squared value of 0.73. So this therefore shows that L-band quad polarized SAR could be used to predict the water table depth, but particularly only the standardized water table depth. For further improvements onto the model, would likely need to have further information, such as multi-sensor approaches to improve. The final graph to show is the random forest approach. We're using the leave location out cross-validation, and this gave an R squared value of 0.66. The benefit of using this model is that leave location out means that it has predicted an area that didn't have any prior information of that in the test set of data. So it's looked at a new location and got able to predict this area. So therefore, we could be able to use this in different locations potentially. The other significant part of our results was that the water table depth can be predicted only if provided it is standardized, which therefore emphasized that there are a lot more spatial variation in the water table, in the SAR signal that are influencing it. So if these values can be eliminated or be controlled, then that would likely improve the model. These values are likely to be the surface roughness and vegetation in peatlands that is causing effect on trying to measure the absolute water table depth. So in conclusion, the quad polarized L-band SAR can be used to predict the standardized water table depth, even at unseen locations. So this gave us our result of an R squared value of 0.66 using random forest with leave location out cross-validation. Further improvements to the model would likely need to be able to use multi-sensor models and to look at other characteristics that are influencing the radar signal, such as surface roughness and vegetation. That's my last slide. Thank you for listening.
Thank you. There's a question.
Thanks for your excellent presentation. So you extracted about 500 polarimetric parameters from 3 ALOS PulSAR images, right? I don't know if you will try to, if you have tried to select the best optimum features and then look into your prediction results if there is, because sometimes overfitting can happen when you use a lot of parameters and you can just select the best ones from random forest that gives the different results.
Yeah, so when it came to using the machine learning approach, we didn't use all the 5,500 values. We did limit it down to only using one value for each parameter. So it was narrowed down to which combination was the most related to the water table depth and for each individual parameter. So therefore, there were only 31 values actually going into the machine learning model.
Okay. And which parameter was the best kind of giving the best results of those polarimetric parameters? Have you done this kind of
Yeah,
analysis?
so the model did have the range of parameters in it. It did vary depending on the different models, which we're still looking into. Some of the models preferred the 2Z parameters, some preferred the Yamaguchi. That's something to look in further to see why there's a difference there.
Thank you.
I have one question. I was trying to get some information from Armando in the meantime. Do you think it would work for wetlands?
I think yes, wetlands are very similar to peatlands. A lot of the work that has done on peatlands has looked at wetlands first, so it could be interchangeable, yeah.
Yes, I seem to remember from working on the land cover map of Scotland that in Flanders Moors there's one area adjacent that was starting to be drained and degraded, right? Is any of these water table depth measurement stations in that area? And have you started looking at if you can use it to detect whether an area is degraded or not, or if there's any big differences?
I'm not sure if the water loggers are in that location. That's definitely something to further look at. And the next step would be to therefore compare if that would happen there. So not yet, but potentially later.
Great, thanks.
Yeah, thanks for this presentation. I was just wondering if you're sure that you do not see the surface, right? Do you see the difference between, because it's a wetland, you know, I assume it's also wet in summer or when the acquisition was done, so which means the soil moisture that you have on top, and how you can distinguish is really that you see the water table beneath. So for me, that's the question, how you can be sure that what you see is the water table and not the soil moisture on top.
That's a good question. That has been, I think, one of the challenges looking at it. I'm not entirely certain. I think my colleague did a lot of the processing to identify which dates to use, so he would be better to ask how they determined it. But soil moisture is something that does influence the water table depth, and something that should be factored for, yeah.
Okay, thanks.
I could possibly add something, co-author. Yes, we are not 100% sure we are looking at the water table. It may be changing in soil moisture induced by the water table. So this correlation is not causation. We don't know if the signal is going down or up because of the water table or because of the soil moisture with the water table. But Georgina is building a model, and finger crossed, we'll be able to decouple the two, finger crossed. So that is the plan, to try to build a model and see if they are decoupable. Are there any more questions? Otherwise, we can go to the next speaker. Thanks, Georgina. Next speaker is Shubhadeep Day with band area mapping using scattering spectrum information from full polarimetry CALOS-2 SAR data.
Hello everyone, good afternoon. So I am Shubhadeep Dey and I am associated with Indian Institute of Technology, Kharagpur. And here are my other co-authors who are Aslin Richardson from British Columbia Wildfire Service, Canada, and Avik Bhattacharya from MRS Lab, CSRE, IIT Bombay. So I am going to talk about the burnt area mapping using scattering spectrum information from full polarimetric ALOS-2 L-band SAR data. So just before starting, I would like to tell that what is the motivation behind this. In polarimetric SAR, especially full polarimetric SAR, we often use many statistical parameters like entropy alpha and isotropy and different other parameters. So here the main motivation is, instead of different statistical parameter, whether we can use only one type of statistical parameter to characterize different targets. And in this case, especially whether we can distinguish the burnt area from the non-burnt area or unburnt area. Okay. So how it works? This, okay. No? Okay. So before going, so if we see the dichotomies which exist in forest fire mapping, so here are this. So in first, the imaging radar was used in the year of 2002 over the boreal forest, where different backscatter intensities were studied. And after that, there are MODIS active fire detection products, which is mostly using the optical-based remote sensing products by Schroeder in the year of 2008. And thereafter, different sensitivities of X, C, and L bands are studied over the Mediterranean forest by Tanase and others in the year of 2010. And it was found that VH polarization, which is actually a cross polarization, is much more sensitive in case of burnt area detection. And later onwards, there was an ensemble projection for the wildfire detection by Wu et al. In the year of 2013. So going to polarimetric spectrum. So as always, we always start the full polarimetric SAR with the 2x2 complex scattering matrix, which is a S matrix, which can be represented as this way, like SHH, SHV, SVH, and SVV, where H and V are transmit polarization and receive polarization accordingly. So from this, we can again form a Pauli basis vector, which is known as K. And from the Pauli basis vector, we can form a coherency matrix. Now, in this case, your V is a vectorization operator on the scattering matrix, and TR is the trace. So from this Pauli basis vector, we can form a second order information, which is a coherency matrix T. And if now, this is a second order information. Now, if we want to know that how is the contribution of this scattering matrix over different polarization polarization mechanism or scattering mechanism, for that we can form a 3x1 complex scattering vector, which seems like this, omega. And then what we are doing here, we are just normalizing the scattering vector, and we are projecting the coherency matrix T on this random polarization or scattering mechanism vectors. And for each of the projection, we are getting another polarization scattering mechanism vector, which we are denoting as omega S. Now, this omega S is actually allows us to project the data onto any arbitrary scattering basis. And in this case, how we can get the arbitrary scattering basis is just by varying omega n for any random omega n. Now, T is a positive semi-definite matrix, so we can say that omega n conjugate omega S, that will be equals to 0. And from there, also we can say that omega S will be exactly equals to omega n only when this coherency matrix represents a canonical target. That means it could be a dihedral, dihedral, or any other canonical targets like a helix or something. Then we are we have obtained this projected scattering mechanism vector, which is omega S, and we are now formulating a 3x3 coherency matrix again using the vector WS by utilizing the inner product with WS into WS transpose conjugate. So in this case, again we can say that whatever we get here, now 3x3 coherency matrix TS, this is again Hermitian and positive semi-definite. So we can perform any sort of polarimetric decomposition or any sort of polarimetric computations as we can do for the original T matrix. Now, just to say here, it's like this TS is now a higher order information. it is actually a fourth order information. So to make it again the second order, we are doing the Schur factorization, and if we do, we are getting another coherency matrix which is TP. Now from this TP, we can get the target characterization parameter theta FP, and for each TP which is we are getting after the projection, after each projection, let's say if we are generating 1000 projections, thousands omega n, we will be getting thousands omega s, and for this thousands omega s, we will be getting thousands theta FP p parameters. So it looks like a spectrum of theta FP. Okay, so if we take a look at this target characterization parameter, which is theta FP, so I would say that this is a intrinsic target characterization parameter. This is not an average target characterization parameter like average alpha, because average alpha comes from the eigen decomposition, and after that you are doing average for all the eigen states. But here we are not doing any sort of eigen decomposition for the theta FP. Instead, it is coming from directly the Hoynen phenomenological theory, which is just a theory between a relation between the symmetry and asymmetry of the target. So it's quite a intrinsic target characterization parameter. It's not exactly an average target characterization parameter. And in this case, theta FP varies from -45 to 45 degrees. So especially the -45 degrees for the dihedral scatterer, and +45 degrees stands for the trihedral or single bounce or symmetric scattering mechanism. Okay, so if we take a look over the image, so here is the LOS 2 Mumbai image of L band, and you can see the average scattering mechanism alpha, and also our previously proposed target characterization parameter theta FP. So you can see that the theta FP actually gives much more contrastive information as compared to alpha over the urban and also over the ocean areas. So if we take a look over the histograms, like for red is for the urban, and green color is for the forest area, and blue color is for the ocean area. So you can see that the separation of the histograms for alpha and for theta FP is quite significant, because for the alpha, the separation between the urban area and the forest area is much higher in case of theta FP as compared to the average alpha. Now, why it is happening? It may be due to the use of the degree of polarization, which you have seen in this slide. Here, MFP is actually the 3D Barakat degree of polarization. So it's not the traditional degree of polarization. It is coming from the concept of the Barakat degree of polarization. Here we are saying 3D because there exists another degree of polarization of Barakat, and it is also 2D degree of polarization. Now here in this case, we are using the 3D parameter. And obviously, if you want, you can also replace this parameter with our newly computed parameter, which is purity parameter. So the purity parameter could be also beneficial as like MFP parameter. Okay, so now if we see our results over RadarSat to San Francisco data, again we can see highly contrastive results for the theta FP as compared to average alpha quantity. And in this case, we have compared it over the oriented urban area. I am saying it is oriented urban area because from the literature I am saying, but it is also a very complex urban area. I mean, it is not like if we deorient the urban area, we will really see that it is exactly an urban area. Even if we deorient it, knowing the orientation of the urban area, we may not attain the same double bounce contribution as the urban area, as the original orthogonal urban area. Okay, so in this case also you can see that the histogram over oriented urban area and urban area, they are a bit close for the average alpha quantity, whereas there is marginal difference, or there is good difference, I would say, for theta FP parameters. Okay, so now if we come to the, this is actually an intrinsic theta FP parameter, which is coming from the actual coherency matrix T. Now, when we project this coherency matrix T onto different scattering mechanism basis, which I have shown omega n, we will be getting several numbers of theta fp as a spectrum. So in this case, we are saying that this is a theta fp p parameters which I have shown before. So if we do it for a dihedral target, then we will see that theta fp p parameters lies exactly at minus 45 degree. Why? Because it is a deterministic target and it's completely coherent. So even if we project the coherency matrix of dihedral, which is 0, 0, 0, 0, 1, 0, 0, 0, 0, this is a coherency matrix of dihedral. If we project it on any scattering basis or any scattering mechanism, we will be getting the similar result. It will not give any other strength on any other scattering mechanisms. So that's why we are seeing only one line at minus 45 degree. Now, if we go for the ocean area is close to deterministic target, which is close to single bound scattering, but depending on different sorts of oceanic conditions like wind speed, tide properties, we can see there are many anomalies also. That's why we see that for this case we have a little bit of stretch towards the dihedral scatterer. Okay, now if we see for the urban area is also a very complex quantity, because even if we are seeing, we are not getting only one building. It's an ensemble of many buildings. I mean ensemble scattering from the many buildings. So we are again getting a higher stress over for this spectrum over the urban areas. And similarly, if we see for the oriented urban areas, this is almost close to your cross-pole scattering or almost close to your vegetative scattering, which we can see also for your random volume scattering matrix random volume coherency matrix, and also the Yamaguchi coherency matrix. Now in this case, please remember that these are the histograms only for single coherency matrix T. This is not an histogram over an entire image. Okay. So in this case, our study area is over the British Columbia, Canada, and I thank Aslin for providing me with the LOS2 data over this forest fire area, and also the ground truth map over the area, same area. So when we have shown different parameters like different statistical parameters, if we see, we can see that entropy is giving little bit of contrast between your unburnt and burnt areas, and also anisotropy is much more contrastive, maybe because of existing of another dominant scattering mechanism, which means that there could be existence of second dominant scattering mechanism. That's why the anisotropy is giving bit higher information over the burnt areas as compared to the non-burnt areas. Now, if we see the alpha, the average alpha quantity, it's not giving that much of contrastive result, I would say. And similar result you can also find for the theta fp parameter. This theta fp is from the only single T matrix. Okay. Now, if we see, you can see that we saw a higher result using the anisotropy, right? So you can also see that from the theta fp1 and theta fp2, there exist exactly two dominant scattering mechanisms. That means there is not a single dominant scattering mechanism which exists in the burnt area. But the theta fp3 parameter, which is the third dominant theta fp, so in this case, how you can get the third dominant theta fp? So you do an eigen decomposition. You have three eigenvalues, three eigenvectors. Now you take the third eigenvector and you make another coherency matrix using the third eigenvector. So after you make the third coherency matrix using third eigenvector, you can again formulate a theta fp using the same formula which I have shown you before. In this case, your third dominant coherency matrix will be of rank 1. Okay. So now if we see using the the classified maps, so you can see using our spectrum, which is only one type of scattering information, but we can generate any numbers of spectrum. And I have found that if we generate more than 1000 spectrum, then the the results actually saturates. But you can generate 1 lakh, 10,000, 1 million, I mean whatever you want. And if we are classifying using the eigen-based parameters, which are your theta fp1, theta fp2, and theta fp3, then you see that there is a bit misclassification. So here I am showing only the overall classification accuracy. So you can see the theta fp spectrum. We got 85% accuracy, and also kappa score is bit stable. And using eigen-based method, it's only giving 74%, around 74%. However, if we are using H, A, alpha, which are 3 different statistical parameters, we are getting 81% accuracy, and using only H and anisotropy, entropy and anisotropy, we are getting 79%. And using only single statistical parameters, we are getting around 60 or 70% accuracies. And also the kappa score is not more. That means the accuracy could be as stable. So coming to conclusion, so it is a work of polarimetric spectrum generation for identification of the forest fire areas. And also polarimetric spectrum is very much sensitive for the targets and could be highly effective for target characterization and classification. So if you are interested, you can also visit, you can also take a look our GRSL paper, which is exactly on this. And there we have shown the land cover target classification with using any unsupervised k-means unsupervised classification technique. So the classification accuracy using the polarimetric spectrum is almost 10% higher as compared to the eigen-based spectrum. And you can obviously use this for our S-band NICER mission, which is our future mission. So I thank you very much for your attention.
Thanks, Shubhadeep. Very interesting. I'm sure there will be plenty of questions. Any question from the audience? Go, Irina.
Yeah, thanks a lot, Subhadeep. I think that's a very interesting presentation and approach. Just if you step now one step back, right? Okay. Because there were some rumors that you can do also HV, right? You just use HV and you compare burnt area and non-burnt area, or let me say forest gaps and non-forest gaps. Did you check also how this compares if you just use a simple polarization to the approach that you suggest with the theta FP?
Simple theta FP only. I mean, are you asking about that if I only use the theta FP parameters and do the classification, right?
No, if you just would use, for example, the HV polarization.
Okay.
Only HV.
Yes. Intensity, okay.
Yeah. Mm-hmm. Yeah, and to compare this, what you get out with...
I have not shown here, but it is with me, and the thing is that it is at least higher than your entropy information.
Okay, yes. But not as good as with
No, not
theta.
as good, yes.
Okay, good. Would be interesting to see this.
Because in case of HV also, what I think, my personal observation is that you are getting only one type of information from the, I mean, it is only the cross-pole information. But when you are going for an incoherent target, it could be a combination of different mechanisms. So what exactly is happening here, like when we are projecting it onto different scattering mechanisms, we are actually getting the strength of the coherency matrix on that scattering mechanism basis, I would say. So that's why, as I have also shown previously, like over the random volume or over the Yamaguchi volume, we are getting a complete spectrum, like which is almost varying from -30 to 40 degree, which is because of this trend. That means that there are existence of also different other scattering mechanisms. As we also see for your PolInSAR case also, that there could be a combination of different scattering mechanisms. So this is happening actually in here.
Yeah, but would be just interesting. Probably you just add, let me say, one line in your table, and it would be interesting to see what is the difference.
Yeah,
thanks.
Okay, thank you.
Other questions? Then I may go with one of mine. What is interesting to see that you change the target, you change the spectrum, your theta FP. Also, I was wondering if you try to combine this information with something else like the purity or the Barakat degree, and to do this kind of two-parameter approaches like entropy alpha in terms of classification, instead of just sticking on one parameter. Have you looked at these plots, theta FP, say purity, for instance? How do they look like? What do you have?
I mean the entropy and theta FP parameters?
Like you plot, you have your, say, theta P, theta FP,
Yeah.
and then you have purity or you have Barakat degree.
Okay. So if I am saying about your, here, let's say in the x-axis you have the entropy parameters, and in the y-axis we have the theta FP parameters. So it looks like it increases initially, and then it again, it has a, how to say, I mean, it has a bounce in at 0, and it actually comes down, and again it rises and goes to plus 45 degree. Okay. So it is little bit complex at 0.
But is there information there to be used?
Yes, because it is exactly 0, because what you can see here, that if you have information at T11 and you have the same information at the T22 plus T44, then theta FP is 0, which is the case of your most of our model volume models. Yeah. And also it is 0 if you have a completely depolarized information. If MFP is 0, so that's why it comes to 0 at the depolarization state, and again it comes back and it goes to 0 again for all the model based parameters. So this is something.
More questions? Otherwise, thank you again,
Thank you
for
very
the
much.
presentation. We can go to the last one.
Yes. So the last speaker is Hochstuhl Silvia, who will present a talk about the multi-frequency PolInSAR benchmark dataset for land cover segmentation.
Yes, good afternoon also from my side. My name is Silvia Hochstuhl, and I'm a PhD student working at the Karlsruhe Institute of Technology. And today I will present PolInSAR Island, a multi-frequency PolInSAR benchmark dataset for land cover segmentation that we generated in cooperation with colleagues from DLR as well as from the Lower Saxony Water Management, Coastal Defense, and Nature Conservation Agency. Well, in the last decades, machine learning methods have revolutionized the automatic image interpretation, which allows applications ranging from face recognition to instant segmentation or textual description of images or videos. One main driver of this success was certainly the open provision of very large-scale labeled benchmark datasets, which on the, like ImageNet, for example, such datasets enabled the training of supervised machine learning models, and additionally, by setting up a challenging task, also motivated many researchers to develop new approaches and compare them in competition. Well, inspired by the huge success in the optical domain, machine learning models and machine learning techniques are already adopted for the analysis of PolSAR and PolInSAR analysis, and already achieve good results, for example, in land cover classification or tree-height estimation. But however, what primarily limits an accelerated speed of these kind of approaches is primarily, or one reason is the limited availability of large-scale labeled benchmark datasets. And with PolInSAR Island, the benchmark dataset I present today, we aim to a little bit fill this gap or take the first step. So I want to start with a short recap of the current situation of benchmark datasets within the PolSAR community. where there are already existing a few open PolSAR datasets labeled by land cover classes, such as the PolSF dataset that contains PolSAR images from various spaceborne and an airborne sensor, along with some land cover classes, the ESA Oberpfaffenhofen dataset, or the Flevoland dataset acquired by the ESA system. These datasets already enable the training and testing of deep learning models and have also paved the way for PolSAR image segmentation based on machine learning. However, these datasets also have several limitations. And the major drawback is that in these datasets, there's no predefined training and test regions. And this mainly limits the comparability of different approaches across the community. And further limitation is that these datasets, the challenges, so the task that is posed in these datasets may be not complex enough, which means we have only a limited number of different target classes, as it is the case for the ESA dataset over Pfaffenhofen and the San Francisco dataset, or due to too simplistic spatial arrangement of the classes, as it is the case for the Flevoland dataset, where we have only rectangular cultivated crop fields. So as a result, we can achieve very high classification performances already with relatively simple classifiers, making it maybe not feasible to evaluate more sophisticated ones, which are needed for more challenging real-world applications. So let's move from PolSAR to PolInSAR. If we look at benchmark datasets in this area, we found out that they are almost non-existent. Despite the combination of polarimetry and interferometry results in a really powerful observation space that can further improve land cover classification. Additionally, current PolInSAR system also allows the simultaneous acquisition in multiple frequency bands, which further extend the observation space. So while there are already some the research in the area of deep learning for PolSAR classification is achieved already first successes and is actively pursued. It is less addressed in the case of PolInSAR data. And one factor that may limit this, or one reason, may be the limited availability of open PolInSAR data in general and the lack of labeled benchmark data sets. So with this benchmark set called PolInSAR Island, we aim to fill this gap. And it stands out from the other existing benchmark data sets due to the following reasons. First, we openly provide labeled multi-frequency PolInSAR data in high resolution. And second, we pose a challenging classification task, which is due to a high scene complexity achieved by mainly focusing on natural land cover classes. And third, we provide a control training and test setting, so it is predefined, which enables the comparison of different approaches across the community. So let's have a more detailed look at the data contained in this dataset. The PolInSAR data were acquired during a measurement campaign in April 2022 over the German Wäldensee, which was conducted using the EFSA system developed at the DLR. And in the dataset that we provide, not all the SAR data acquired in this measurement campaign are included, but only data sections that cover the area of Baltrum. As you can see on the figure on the right-hand side, we used two overlapping flight paths that were acquired in opposite flight directions. Well, the EFSA system allows the acquisition of fully polarimetric SAR data in 5 frequency bands, and the data included in this data set were acquired simultaneously in S and in L band. The incidence angle interval that is used to capture the selected image scenes ranges from 26 to 58 degrees. For to enable interferometric analysis, a repeat pass configuration is used where the selected area was captured twice with a time offset of 12 minutes and a vertical baseline of 40 meters. So on the right-hand side, you can see the imagery of the data set. So in the first row, the color-coded images according to the Pauli decomposition, and below interferometric coherences in VV polarization, just to give you a first impression of the data included in this data set. The data is so based on the co-registered interferometric image pairs. The PolInSAR coherency matrix is computed for each pixel, containing the polarimetric and interferometric information. And in a pre-processing, in a post-processing step, the flat Earth space is removed, and the resulting representation is projected from slant to ground range geometry on a 1 meter by 1 meter grid. So the final data set that is provided contains 4 image products in total, so 2 for each flight path in S and in L band. So now to the question, how do we get the land cover labels for these data? Because actually we do not have reference data acquired on the same date. So that is why we use the semi-automatic workflow for labeling, which is shown here, and I will describe it step by step. So to realize a fine-grained segmentation or fine-grained labeling with a high level of semantic detail, we used an existing biotope type map that was provided by the National Park Authority of the German Wendensee. This map, which divides Baltrum, which is mainly covered by natural coastal areas, into 40 different biotope types that are all listed here. However, this map was generated in 2013, thus 9 years before our measurement campaign. Thus, significant changes in the extent of the different biotopes are to be expected. That is why we revised the map in the following way. The first step, buffering and filtering, aims at masking out areas where the biotope type map, so the classes in the biotope type map, are very unlikely to match the actual land cover. And it is assumed that this is particularly the case at class borders. Furthermore, we also added some manually generated labels for the classes water and tidal flat, because these 2 classes are highly dependent on the time of acquisition. In the following processing step, class merging aims at grouping the biotope types to more general classes. So because first we have these 40 biotope types, which are with really, really high semantic detail, but also we have only very, some classes where we only have like 100 pixels. So that is why we did a grouping to more general land cover classes, and the requirement for these target classes were that a separation of the classes is possible using the PolInSAR data, but not too trivial. And to determine an appropriate grouping of the biotope types, we performed a visual analysis of class separability. And to do this visual analysis of class separability, we first extracted a multidimensional feature vector for each image pixel just by extracting different polarimetric and interferometric features and stack it to a multidimensional vector. And to visualize this multidimensional feature space, we performed a dimension reduction using UMAP. So this actually just aims at preserving the local and global relationship of the data, which in this application corresponds to the similarity of the selected PolInSAR features. So at the end, we can represent the data in 2 dimensions, which we can then visualize. Such a scatter plot visualization is shown here for the data set. And in this plot, the data points, which corresponds to 1 image pixel each, are colored according to their membership into 6 generic classes. This class division listed here is chosen manually by just grouping the fine-grained biotope types based on their semantic meaning. And in the scatter plot, we see that separability of these classes is more or less possible. However, the 2 classes, dune landscape and salt marshes, are composed of many different biotope types, and that is why they are further investigated. Well, let's have a look at the class dune landscape. For classes belonging to the dune landscape, we computed a new embedding that is shown here in the middle. Now, all the data points are colored according to these fine-grained biotope types. And what we see is that the classes white dune, which is shown in yellow, the big group gray dunes in gray, and peat bog stand out as distinct clusters. The other biotope types strongly overlap due to very similar polarimetric features. But we could recognize some grouping, so we could see that biotope types belonging to the more general class dense high vegetation can be separated from biotope types of coastal shrub. So we summarized the biotope types to these 2 classes. Similar investigation is done for the salt marshes, which consist of 4 different biotope types. Here we decided to separate them into couch grass, upper salt marsh, and lower salt marsh. So in the end, we end up with 12 target classes that are shown here. So now all the points are colored according to this 12 target classes, which are the final classes for the benchmark dataset. So then we come to the last step, the manual refinement. That is done realized by a visual interpretation of PolInSAR image features, as well as of optical images that were acquired just 1 day after the EFSA measurement campaign. So after re-rising and adjusting all the classes, we end up with our final label class, our PolInSAR Island class map. So well, after that, the whole data set is, of course, divided into disjoint subsets for training and testing. And therefore, we used a chessboard grid. And we used this strategy because we wanted to make sure that classes that are spatially concentrated on the island, like you see for the violet peat bog class, are represented both in the training and the test set. And additionally, the strategy also ensures that for all the classes, the entire incidence angle interval is covered as well. So along with the dataset, we also provide some results of some classification results of established algorithms that are intended to serve as really the minimum baseline for this dataset. And one of the classifiers, I will just show it in shortly. It's just a random forest classifier trained on different polarimetric features. So a pixel-based classification is performed. And yeah, the results will be also published along with the data set, as I said, just to have a minimum baseline for further classification. So to sum up the presentation, PolInSAR Island is an open, labeled, multi-frequency PolInSAR dataset for everyone who wants it to use. And But of course, there are also some limitations of the dataset. One is definitely that we have label gaps, so we don't have a seamless labeling of the whole region, which just wasn't possible without more reference data. And this dataset is also just focused on a single sensor and a single location, so it's classifiers trained on this dataset won't be easily transferable to other sensors or other locations without further adaptation. So the intention of the dataset is not to be able to train universally applicable classifiers, but rather to have a dataset which allows the training and testing of machine learning models or some other models, so it's not just intended for machine learning, can also test other algorithms. But what was important for us that we have an open data set and a controlled training and test setting so that we can compare approaches across the community. So then convenient access to the data is given via the KIT Open Data Platform, which you can reach by scanning the link, or I just posted also the link in the conference Padlet. Oh, it doesn't work? Okay. The link on just you can't scan the QR code. Okay, then you have to use. So that's why I also posted the link in the Padlet. Maybe you can try this. I already saw that there are some issues with the KIT repository sometimes. So if there are any issues, I'm here and will fix it.
Thank you. Thanks for presenting. It's great to know that we have these data sets available so we can use as a test bed. Are there any questions from the, I'm sure there will be questions from the audience. Yes, please, Vaid.
Just out of curiosity, I guess the main goal is to build this data set, so it's great with the EFSA system. So it's just, have you tried or do you plan to try also the approach over data of satellite missions?
It would be nice, but I honestly have to confess that I think that I won't do some of this labeling process again, because it's a lot of work, and that is why I wanted to publish it, because I thought, okay, I had it just took a lot of time and just to sit there and labeling, and it's a really boring task sometimes. And so it would be nice if there are more data sets like this also for satellite data.
Okay,
of course.
Thank you. Thank you.
Thanks for your presentation. I'm happy to see that someone from the radar community has thought about working on this benchmark data. Because normally, computer vision people, I feel that there is some knowledge gap. But the question is that, because I think you mentioned, are you going to extend this kind of data set or provide other benchmark data? Because it's just a very limited case study that you can use it for training. And it's not easy for everybody in the radar community to do transfer learning for other cases or other areas.
Yes. So the only thing I really plan is maybe to also add some other data from the same measurement campaign, because that's the only data I have at hand, and I'm able to label it in more or less time.
But of course, this is very challenging, because when you want to use the other data set, you have to consider exactly identical configuration in other areas. So, and then transfer learning is a question.
That's what I also said in my conclusion. I'm aware that you can't just train on this data set and then use it for some other sensors without any adaptation. So that's why it's really just intended to try different algorithms and different approaches and to compare them in a controlled environment.
Okay, so why not to use the satellite-based data set, like, for example, future biomass mission, that you could do similar thing? Because that is very...
it would be nice.
Are you thinking about that? Maybe that you can do similar thing in future?
Honestly, I'm not sure if I want to do such work as for labeling in the future, but yeah, what would be nice if there's some platform where we could collect all the data, all the benchmark data sets, because I see in many times that somebody have a talk and present some results, and they all labeled the data for themselves. So there are a lot of labeled data, but it's distributed over the whole community. So for example, in the last talk I saw there's a perfect data set, and they say, oh, okay, we have also land cover class map. Yeah, perfect. Just start and collect all the data somewhere.
Thank you.
Yeah, I also will agree with you. These transfer learning type of things are powerful weapons that if you use bad, they will shoot you on foot. So you need data sets. You cannot just take this and then plug to detecting something else. Like incident single effects that you see here, you won't see in satellite, for instance. So there's a lot of things that is, you cannot just, this is a test bed, one of the many, hopefully. But it's very great that you were working on that. Any other questions, final questions on regarding this talk? Otherwise, thank you for the presentation. Also, I would like to thank you, all the speakers. Very surprisingly, we stick to the time. And I think it's not because of the work of the chairman, the people, but it was the work of the people presenting. They've been really good at sticking to the time. And I did say I really enjoyed this series of talks here. And it's also nice to see that we are dealing with things, topics, applications that before were a little bit niche. Like the bogs, we have the permafrost, we have the tidal floods. It's all good stuff to see that we are spreading the application of SAR.
Potentially new sessions in the next PolInSAR.
Yeah, indeed, these new trends. So I think Magda agreed that there's still a bit of time for picking your brain in case you have some recommendation related to the two last sessions. So the one on agriculture and this one. Is there anything you would like to say, to add, to comment about that you have seen or that you would like to have seen, or generally that you would like to report to ISA for the future? So, of course, you can use Padlet, but since you are here, if you, you want to... Something you think it should have been there, like an elephant in the room, was not there. Somebody should have presented these things and it's not there. It's an issue that we all face and a common challenge.
I think first of all there was nice comment from Elise about the SLC cubes, SLC dataset on platform, and actually this is something that is going to happen also in the platforms of ISA. There will be ARD SLC dataset, so this is something that is ongoing. But this is nice comment, and I think it would be highly appreciated by larger community, not only PolInSAR community, but also INSAR community. So this is, I think, nice comment.
If I had to add something coming from the last presentation, it would be nice also to have this labeled data shared with the data set. I don't think at the moment all these data that ISA shares, the third-party mission, they come with metadata, but not with labels. So if we could have that as well, it would be an extra layer. It would be really cool. Any other comments? Yep, please.
Yeah, to elaborate more on that point of making this labeled data, that's a problem, I think, generally with remote sensing. We have lots and lots and lots of data, and it's ever increasing, but the problem is finding and better using this reference data, and ideally not having to spend months of your time collecting it yourself. So is there scope, for example, for this data to be cataloged in a common format, maybe something that can be coordinated through ESA, or put, for example, in the map for people to easily explore and playing with?
Coming from Baid?
Yeah, it's true that we are in the golden era of artificial intelligence and golden era of open access SAR data, but I have learned something before, that remote sensing without the labels data is remote non-sensing. So I think we need a lot of efforts to make such a label data like in other computer vision tests, to test a lot of algorithms in computer vision or deep learning for our own applications.
Any other points?
Yeah, sorry. Thinking about also what we were talking about in the other session, in the biomass session, and they gave a nice talk, and they spoke about how doing this GeoTrees initiative, how much it gives to kind of the rigor and the validation of the data, and how it really only, on the total compared to the cost of the mission, is only a fraction of the cost. And if it, for other application, if that could be something that can be included as keep 5% or 2% of the budget to collect reference data, to collect things to a company and make the data more accessible and easier to use.
Any more comments on this point? I've been told that we have time, so there is no icebreaker yet, so we have time for, it's not that I'm keeping you here because I'm bad. So another thing that it was quite interesting to see is this, in the agricultural session, most people were using Sentinel-1, and I think this is witnessed the fact that you need time series for working on agriculture. Will people agree with me, or you think that Sentinel-1 like maybe quad-pol is not what we need in agriculture? We will need a different frequency or whatever, a shorter time frame or whatever, so the time span. So what is your view? Is it Sentinel-1 a very good solution, or we need something else for working in agriculture?
Thank you. Agriculture is a very wide field. It depends on what you look like. If you like to see where potatoes grow, then maybe Sentinel is good. Yeah. So if you try to find the soil moisture of the vegetation layer, then Sentinel-1 is crap.
So would you prefer an L-band system, but with the same repetition of
again, for what?
Mm-hmm. Any more comments related to the agricultural session? Another one that was quite interesting is the one on urban area. That is the compromise between resolution and quad-pol. That is a cool thing. Is Elise still in the room? Mm-hmm. So I don't know if you want to add anything about that, or so still quad-pol is important, right? Or this was your, but resolution too. So what would be the compromise? Or is there a compromise, or we just need a high resolution quad-pol?
My opinion, but it's just my single opinion, is that quad-pol is important in the case of dynamic analysis. especially when you are considering deterministic targets in urban environments, because my experience is that when you do not consider one polarimetric channel, you lose all the targets that are answering in this particular polarimetric channel. But for natural targets, I'm not so sure, I would say so.
Anybody else would like to comment on the urban area applications? Another thing that I think, since we have this floor now open, and it's the time we can have a wish list, we do this every year. But is there any wish list that you would like to have with this in terms of third-party missions? Do you think what we have is good enough? We should have more? Or besides what we already have? Is there any comment on that, or we are happy with what we are given at the moment? Elise, please.
Just one additional comment is just that this morning during the agricultural applications, we have seen that there are a lot of works that are considering such dual pole entropy, or it's exactly the same information that is contained in the degree of polarization. That's quite the same. So what I want to highlight is that we need, we still need the cross product between the polarimetric channels when they are available. Even if we do not have the full polarimetric information, there is this information in the second order statistical moments in HH and HV or VH and VV. Which is very important, and once again, most of the time, I guess that perhaps some people do not use them because they are less available, I would say, in an easy way. As soon as we are dealing with the GRD projects, for example, we lose just this part of information, and it's a pity because it exists, so please use it when available.
Very good comment, thanks. Any other points people would like to add? One thing that I would like to pick your brains about is related to SAOCOM. Now we have the SAOCOM available. Are people using them? And if not, why? This quad-pole L-band SAOCOM data. Somebody from CONAI here? No.
The guy from CONAI and Santiago is in the other room.
Ah, okay. Oh, okay. Yeah. Okay, then I guess I can give my experience with that. I think the problem at the moment is to read these top SAR images because there is no way of reading at the moment. There is some issue, but I see it at quite cool things to have these images provided we can read them, because they have a quite well cover of Europe. I've seen, for example, I'm interested in Scotland, and these hundreds of quad-pole images there. Also repeat, not just one single acquisition. So it's a wealthy data set, but we need to, Francesco, we need your help to get this this reader.
So you can apply for this data for free. Of course, you cannot get for thousands of them, but if you need a subset of data for research, you can apply easily via ESA. You can also apply directly to CONAE. And if the data are over Europe, then you have to apply via ASI, Italian Space Agency. But everything is written on the PUMAS website of ESA. So profit of this opportunity. There are quad-pole data in L-band, and they are quite powerful for new applications. And I would really encourage you to take advantage of this opportunity.
So with the risk of being your worst enemy now, I see they're almost ready, but not yet. So I can put another point to talk about. So there is now this developing with MAP and also translating PolInSAR Pro into Python. Are there any comments from your side in terms of what we should have inside this PolInSAR Pro Pi for the next stage? This first stage is written, as is what you have seen, but do you have any recommendation that are different from the recommendation from 2 years ago for the second stage of PolInSAR Pro Pi, or whatever will be called? Or you are happy with what was set, what you saw in the slides on the first day? There is somebody at the back.
Once again, sorry. Perhaps we should anticipate the fact that most people involved in artificial intelligence algorithms will be able, perhaps soon, to use this kind of images. Up to now, it is difficult because we know that the preparation of the datasets is a difficult point. And perhaps we just have to think about what will need people using this kind of images for machine learning algorithms, for example. I don't know, perhaps on the size of images that we create automatically or from the different Polarimetric parameters, I don't know. But
so do you mean there should be some routine that applies some machine learning methodology?
Or at least to create easily data sets ready for machine learning tools after, not to include machine learning tools in PolInSAR Pro, but just thinking about the way of creating easily big data sets.
So having a way of, say, storing images or whatever that is quite consistent and easy then to feed in, like a cube, an X cube, this kind of stuff, right?
This would be the idea.
Yeah, that sounds very good.
Actually, there is, I remember, a recommendation from the last PolInSAR about encouraging the use of machine learning into Polarimetric tools. So maybe this suggestion could be used to complement or integrate that recommendation. Indeed, it's something that we have not been doing yet in ESA, as far as I know, but it's something that we might do also because we are analyzing the application of artificial intelligence, machine learning in many type of processing and applications for remote sensing. So polarimetry should be one of those.
Are there also any suggestions in terms of formats that we should use? Are you happy with Snap or PolInSAR Pro binary type of format? Would you like them saved as GeoTIFF? You like them as X cubes, or you don't mind? Is it the same? I guess people don't mind. Also, a little bird a few days ago told me that we should probably move away from coherent decompositions. I support these things. Maybe for the second phase, developing all this coherent decomposition, not very much used. Maybe we can do other things instead. Is this also the thought about the audience that maybe investing time in the second phase on coherent decomposition could be better invested in developing different things from PolInSAR Pro? Or it's just me and the bird that think that? No, I guess it's okay.
Thank you. I think it's a bit a question of perspective. You like to use PolInSAR Pro to teach your student how many decompositions are out there, or you like to use PolInSAR Pro to access the information content which is especially given in polarimetry. Yeah, so if you see the presentation today, people treat polarimetry as one another channel. So as a multi-frequency channel, as a multi-temporal channel. So it's missing this exploration of the special polarimetric information content. Of course, this is partially also because of the poor sensors. If you have only co-cross, then you have 2 in densities only, then the limitation, except if you are in urban areas as Elise, then you can explore this. But the rest is crap. So this means that with biomass will come a sensor which provides polarimetry for forest. For agriculture, remains crap, but for forest, you have something. So if you think that you can have PolInSAR Pros will be there to explore the extra information content of polarimetry, then one more decomposition makes no sense. Then you have to think, what is this which makes polarimetry special? Where are the data for this? And it will be forest and biomass and maybe also ice, and then start to think in this direction.
It's a very good point. So there's a raise of hands. How many people think they will be using this new Python code, PolInSAR Pro derived, for education, or how many people think that they will using it for more operational things inside their stack? So many people will go for the education bit. It's 3, 4. How many people go for the operational one? It's 10 people. Yeah. So I think it's mixed again. You cannot be decoupled fully. But yeah, it's, I do see absolutely your point. Can I volunteer, Magda, you, that if you have idea or suggestion about which algorithm would you like to see from PolInSAR Pro converted to Python in the next stage, so in about an year, you drop a mail to Magda so that she can collect this information.
And also for algorithms that are not yet in PolInSAR Pro, so it could be also...
Yeah, exactly. Also for things that are not yet there, but you want to add. And I think, for what I can see, it will be an open community endeavor, so people will be able to share their code, will be included, like map, you share their code, will be included.
Yes, but I mean, all of this work that we do, you can use also locally. You don't have to use it on map. No, you can. So it's not only we say it. We re-implement it to use on map because we know that there will be a lot of data, quad-pol data. We can process there. But of course, this is all on GitHub, available on GitHub, so you can download. Upload to your local environment and play with your data.
So any final comments that you would like to add, or things that you like to see written down as a recommendation for the next PolInSAR? I guess yes, one there.
Yeah, so I'm from North America. I'm not sure it's my own issue or something I don't understand. So I'm wondering, PolInSAR Pro and Snap, how does two software connect? For us, we process the covariance matrix, and then it ports to PolInSAR Pro. So we have a problem for terrain correction. So I do not find any function on PolInSAR Pro for terrain correction, and there's not a lot of decomposition implied on Snap. I'm not sure in the future, the next step, so they will combine some functions together to Snap, or just develop the more function with PolInSAR Pro, like terrain correction.
That is a good point. If something is missing from Snap and PolInSAR Pro both, it could be developed in the future in MAP or generally in this set of routines. So if you have a specific, you said the orientation, did I understand well? That could be definitely one added to the next stage. Yeah, definitely. Thanks for the suggestion.
Yeah, I think as far as I know, there is nothing about change detection and target detection functions in PolInSAR Pro. Yeah. And the second thing is that I think still it's not possible to show what some parameters inside the PolInSAR Pro. You have to use some other tools. You export it to Snap or some other software to geocode them. For example, I tried to extract the Shannon entropy inside PolInSAR Pro, but if you want to get the GeoTIFF, it's not possible. You have to use some other softwares. And also about the SI Snap, I think there was some Python library named SnapPy. I used it 2 years ago, but there was some problem with that, and it's not some kind of very friendly tool. If you want to use it for operational services, that I think it will be easy that you just give the set of SLC images with some certain parameters without taking care of about other things for operational service, and get GeoTIFF or radiometric or sigma not backscatter or MLC as output. And also my other recommendation for PolInSAR Pro is I think we don't get RTC-based covariance matrix data, right? I think it's sigma not-based covariance matrix or covariance matrix. It's good to have gamma not-based covariances.
That sounds really good. If you could write it down and report, then it's good recommendation. Yeah, in the Padlet or
okay, yeah, I will make it there.
So I think the icebreaker is now ready, and you'll be glad that we close it here, the round table. Francesco wanted to say something, sorry.
Yeah, so you see, yeah, I will be quick. Some young people here asked me about opportunities for research postdocs in ESA. I mentioned that the first day, but they didn't give any concrete links. So maybe now in a few minutes, I will just show you which are the opportunities that we offer for young scientists in ESA. So, okay, on top of the training courses that we do all the time, we just finished, for example, the Polarimetry course last week in Toulouse. Then DLR is doing the online courses in Polarimetry. But we also organize continuously, almost all the time, a series of new training courses. And then either you come in presence or you can download the material from the websites. But please have a look constantly in these web pages, the EU4 Society, where we publish all the opportunities we create all the time in terms of training courses. We also develop massive online open courses, and in particular we have one which is constantly open about SAR. It's called Ecos in Space. It's done together with the University of Jena, and now we are creating the new modules to be added there, and it will be also about biomass and hopefully polarimetry, which is not yet part of it. So this is also something I think very useful and relevant for most of you or for your students. We have opportunities for young scientists to come and work in ESA. So we have internships, national trainees, and also postdocs called research fellowships. These are for 2 years, and these are for people either from ESA member states or cooperating states. So not yet member states, but already cooperating with ESA. And come and ask me if you are interested in this. We also, so I will skip this. We also have recently opened the Earth System Science Hub in ESA. It's a new lab where we host researchers, people who are quite autonomous already in research, so not really for students, but people who are in the, they completed maybe their postdoc and they would like to stay in ESA for 6 months, 1 year, and we offer opportunities to be with us and cooperate with us and with other scientists. So this is mainly for people from ESA member states, but again, also from outside ESA, if your country has some cooperation agreement with ESA, we can involve ESA external relations and try to host also people from outside ESA member states. And then finally, for those who are interested in machine learning and artificial intelligence, we also have a lab. It's called the Phi Lab, where people are working, doing research about the application of machine learning and artificial intelligence into Earth observation, remote sensing processing. So, for example, what you just mentioned for polarimetry, and then you can also apply there. So if you have any questions, please come and see me. I will be here until the last session of Friday.
I thought not to speak. I'm super impressed.
Why?
Because there is no perspective in things what you can do in polarimetry. There is no discussion about the quantitative advantages. You go to assess moisture in vegetation, you need polarimetry, otherwise you have no chance. And you treat it here, you know, as if it is, I don't know, a Landsat channel. And this culture is not here. And then you should kick them. You say, not nice. So we need to have this. No, I will do, but...
And I would like you...
No, I will do this point, yes.